Good evening to all. Today is the 5th day of our ATAL online 6-day faculty development program. Today we have two interesting sessions, right? That is, so the first session will be handled by Dr. S. Satish. He is an assistant professor, MIT, Anna University, Chennai. The title is Synthesis and Characterization of Functional Nanomaterials. The second session is on design, fabrication, characterization, and mechanical performance of thin-walled metallic components using wire arc additive manufacturing. This session will be handled by Professor S. Sivashankaran. He is from Qasim University, Saudi Arabia. Before starting the session, let me introduce Dr. S. Satish. Dr. S. Satish is an assistant professor in the Department of Production Engineering, MIT campus, Anna University. He obtained his PhD in Production Engineering Department from National Institute of Technology, Tiruchirappalli, and ME in Manufacturing Engineering from Anna University. His research interests include additive manufacturing, advanced materials, composites, friction stir welding, and tribology. He has more than 15 years of academic and research experience. He has published more than 34 papers in reputed SCA journals and then many papers in Scopus Index International journals. He has authored book chapters, filed patents, and obtained copyrights. He has delivered invited lectures, chaired sessions in many conferences, and organized funded projects and international conferences. His benefit aerospace, defense, and biomedical applications. Another important thing is to publish patents in IPR. Has published many patents. He is conducting workshops in many colleges, and he is a mentor for colleges. On behalf of you all, I welcome Professor Satish to handle the session. Welcome, sir.
Thank you, sir. Thank
I
you.
will hand over the session to Dr. Satish.
Thank you very much, sir. Sir, the screen is visible, sir?
Yes, sir. It's clear, sir.
Yes, sir. Yes, sir.
Sir, the slides are moving?
Yes, sir. Moving. Sir.
Yes, sir. Okay, sir.
No, sir. The slide
Okay,
is
sir.
not moving.
Now, sir?
It's moving now, sir. It's moving.
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
It's moving, sir.
Okay, sir. Right, sir. Okay, good evening to all. So, first of all, I have to thank Dr. Palnichami, sir, and the management for giving me an opportunity to present a session on this faculty development program, ATAL sponsored faculty development program on futuristic manufacturing with 3D printing and digital fabrication. In the titled Synthesis and Characterization of Functional Nanomaterials. So before going into the session, let me just introduce about our university. So actually, the Anna University will be constituted by 4 different campuses. So as you have been aware of this, College of Engineering, Madras Institute of Technology, Alagappa College of Technology, and School of Architecture and Planning. So then the institution will have 34 university departments, 5 national facilities, and 59 autonomous centers. And the university was accredited with the NAC A++. Also, it will have a QS ranking. In coming to NRF ranking, it will have an overall 29th institution. And under each category, it will have good rankings. Then, when come to MIT campus, the following courses have been offered. Following programs will be offered from Anna University, MIT campus. So this is about the department, brief milestones that will be obtained by the Department of Production Technology. Then coming to the courses offered under the Production Technology will be B Production Engineering, B Robotics and Automation Engineering. Then ME Manufacturing and Mechatronics Engineering. So coming to the presentation, so what is nanotechnology? So I hope now we people are been moving towards the nanotechnology. So before moving to going to nanotechnology, let me know what is nanotechnology. So when we discuss nanotechnology, each and everyone will have a separate definitions under our own perception. So it's similar to that, different organizations have categorized what is nano and what is nanotechnology and what is nanomaterials. So when you are coming to a nanoscale, so the British Standard Institution has defined that when a particle size ranges from 1 nanometer to 100 nanometer, so that will be called as a nanoscale. So when a nanotechnology, when it can be called as a nanotechnology, the technical committees of the International Standardization Organization has stated that the scientific information used to manipulate and control nanometer to exploit its size and structure, specific feature and properties that are different from those of individual atoms or molecules or bulk materials, that will be categorized as a nanotechnology when it will be focused under 100 nanometers. So this will be called as a nanotechnology as per technical committees of International Standardization Organization. Whereas the European Patent Office has stated that describes that the entities with a controlled geometries under 100 nanometer, that at least one functional component in one or more dimensions that can lead to size dependent physical, chemical or biological effects, that will be categorized as a nanotechnology. When coming to American National Standard Institutes, so understanding the controlling matter of approximately 1 to 100 nanometers in size will be categorized under nanotechnology. So three different things, but anyhow, it will be fixed to a range of 1 to 100 nanometers. Whereas the nanoscience will be deals that study of nanoscaled matter to understand their size and structure dependent features and to compare individual atoms or molecules or bulk materials related to differences. This will be called as a nanoscience by British Standard Institution. In similar way, nanomaterials will be defined as the materials that have one or more dimensions, external dimensions, an internal structure in the nanoscale may display novel features compared with same material but not in the nanoscale. So here the nanoscale will be less than or equal to 1 and greater than or equal to 1 and less than or 1 equal to 100 nanometers. That will be called as a nanomaterials. So in a similar way, European Commission also defined that so insoluble or biopersist purposefully produced material under 1 to 100 nanometer size, that can be called as a nanomaterials. So one more thing by European Commission and then European Commission for Novel Foods. So all these things will be defined the nanomaterials in different way, but anyhow, it will be in the range of 1 to 100 nanometers. So apart from that, engineered nanomaterials, if purposefully a material will be made in order to obtain a nanometer level, then it will be called as a engineered nanomaterial. And in same way, nano object, when a material with one or more peripheral nanoscale dimensions, that will be categorized under nano object by British Standard Institution. In a similar way, nanoparticle, nanofiber, nanocomposite, and nanostructure and nanostructured materials will be defined by British Standard Institutions, as mentioned here. So, do we think that these nanomaterials or nanotechnology is being developed recently? So, if you arise a question, so definitely the answer will be no. So, though we have been focusing on nanotechnology, or we have been highly relies on nanotechnology in recent days, but without knowing that whether it is a nanotechnology, so people in the ancient time periods have utilized these nanomaterials in their existing practicals. One such example which will be identified will be the engravings or the paintings that will be observed in the Chowad Pond Ark Cave and Lascaux Cave. these two caves, the paintings or the engravings are that will be observed in these two caves picturized here. So these pictures will be relates to the animals like lions, mammoths, bears, owls, like that. So these are all the pictures that will be engraved in these two caves. So there are when you have been looking into this Chawat cave, over 1,000 images have been observed in these caves. And when come to Lasak's cave, nearly 600 painted animals and 1,500 engravings has been observed. So when you have been looking into these engravings or paintings, the material that will be taken as an samples from these engraves, and it will be put into the examination, and they have been observed that these are all the material that will be obtained through the uh, uh, smoke and soot of fire contaminants, which is nothing but as we have been burned a charcoal, and the charcoal will be used for engravings. As we people have been, when you have been during the childhood, we have been engraved with, or we have been just scribbled with these charcoals. So similar way, some of the smoke and shoot out fire coals, that is the coals has been obtained, that will be utilized to make the engraves, whereas which will have the particles of nano. So these nanoparticles will be resembles with the carbon nanotubes and then fullerenes and graphene. So this will be nearly, hope it will be around some thousands, 16th or 19th centuries. So it will be observed in such a time period. So even at that time itself, the nanomaterials have been used by our ancient peoples. So next one, another thing that will be observed in the as a nanomaterial, which is nothing but the paintings that will be found in the Egyptians. So where the paintings, you can able to visualize the painting here, two different paintings which will have different colors. So these different colors, when you have been looking into the particles that will be taken as a sample from these paintings, and when it will be put into the examinations, it will be observed that it will resembles with the nanoparticles. That is the blue color, the samples that will be observed from this blue color painting. It will shows the nano sheets. So the electron microscopic images that which will be picturized here, that will show the resemblance of the nano sheets having a 5 nanometer thickness. And in addition to that, some other particles that will be observed in the paintings will be glass and quartz. So these are all the things that will be evident that the nanomaterials will be utilized by our ancient peoples. And then the fabrication of palladium sulfide nanoparticles, which will result in the outcome of the nanosheets, which will be 5 nanometer. So that will be used as ingredients for hair colors. Whatever the color that will be pictured is here, black color, that will be obtained from these palladium sulfide nanoparticles. So another evidence that will prove that the nanomaterials will be used in the ancient time period. So here we will be visualizing a Lycra gas cup, so which will have two different colors when it will be subjected to a light under light. So when it will be subjected to a light, it will have a different color. When it will be exposed, when it not exposed to a light, it will exhibit some other color. So as you have been visualized in A and next image, when it will be put into a light, it will be exposed to a green color, whereas when it will be exposed to from the back of that, so red purple will be observed. So this will be the thing that can be made with the help of copper and silver nanoparticles, which will be in the range of 5 to 100 nanometers in diameter. So this is one of the oldest cup that will be made with the dichroic glass, that made the material glass to have two different colors, that to exhibit the two different colors when it will be subjected to two different wavelengths of light. So then another evidence that will be picturized here, that will show ancient church window, so which will have nanoparticles in that. So whatever the colors which will be picturized here will be identified with the same particles like silver and gold, but depends upon the particle size that will be utilized to create such a paintings or glass windows. So depends upon the particle size, it will exhibit different colors. So when these samples that will be collected from these windows, church windows, will be put into the electron microscopy. So it will exhibit images, microscopic images, as it will be picturized here. So the size, particle size, gold of particle size 25 nanometer, which is resembles with the spherical shape of the particle, and it reflects the red color. Whereas the similar gold particle, which is having a 50 nanometer in the spherical shape, will have a reflects a green color. When it will have 100 nanometers, when that will have a color of orange color. So when you have been taking silver particles from yellow color and blue color and red color, so it will exhibit a different particle size. So this shows that these silver and gold particles, which will be utilized in these church windows under different colors, will be have a same particle, two different particles, and a different particle size with different with the same similar particle size. So this evidence that the ancients will be utilized the nanomaterials. So another evidence that shows or proves the utilization of nanomaterials in the ancient time period. So this will be the saber or sword that will be made with the Damascus steel. So this will be when you have been taking a sample from the steel, and it will be subjected to the investigations. So the material will be collected and it will be dissolved in the hydrochloric acid, and which will be put into the examination, which will shows the nanowires, cemented nanowires. It will be in the carbon nanotubes, which will have a size of 5 nanometers. So these are all some of the evidence that shows that the nanomaterials have been utilized in the ancient civilization. So apart from this evidence, you can able to observe that the particle size, the nanoparticle size, then the morphology and the texture, it will be that will highly depends or highly affects or influences the property of the materials in which it will be. Particularly while we have been focusing on the functional nanomaterials. So in specific, if you want to have attain a specific property, in such case, the nanomaterial will be the best choice to create or to obtain such a kind of specific properties. Hence, this will be called it as a functional nanomaterials. Apart from the conventional regular utilization or regular tailor-made materials, the in specific material property can be obtained with these kind of nanomaterials. That will be proven that from the ancient applications, it will be proven that the nanomaterial will be a right choice, and it proves that it can be utilized under different scenarios and different applications to have a specific property enhancement. So though we have been knowingly or unknowingly, we have been utilizing nanomaterial in different applications, but the nanoparticle or nanomaterials will be comes into picture in a scientific way from the 1857. So this slide shows the historical developments in the nanomaterials. So in 1857, Michael Faraday studied the fabrication and the features of the gold colloidal suspensions, where it have the nanoparticles. Then in 1905, that is the origin, where they have been found that the compound, sugar compound will be in the range of 1 nanometer. So further developments in the technology, that is the electron microscopy, arrival of electron microscopy helps to understand and identify the nanomaterials in a better manner. So such developments leads to the observation of carbon nanotubes in 1952. Then in 1959, the nano related talks, that is in a common science forum, will be comes into picture. That will be by Richard Feynman. So he has been put into the global science forum. Then in 1981, the nanotechnology name was coined by Taniguchi. So he has been the person who has been first, he has been made the nanotechnology term. And then in 1981, the invention of STM, the scanning tunneling microscope, will be comes into picture. That will support for the further further achievements or further investigations of the nanomaterials. Then from 1985 to 87, the invention of atomic force microscopy then made the nanotechnology for the next level. Then the fullerene identification, discovery of fullerene has been made during those periods. In 1990, the first issue of journal relates to nanotechnology has been happened in 1990. Further, in 1991, the carbon nanotubes have been elucidated. And then further in 1997 to 1999, nanowire circuit has been developed by HP. And then nano switches has been made and different nano transistors. So further technological developments on the development of specific applications has been made in the 1997 to 1999. In 2000, the first PhD program in nanotechnology has been given, and then first transistor has been put into utilization by IMB and Delft in 2000. Then in 2003 and then 2004, further continuity of 2007 and 2009 made a remarkable notice in the nanoparticles, particularly the nanoparticle implementation of nanoparticles in the drug delivery systems. So these are all the things that will be picturized in the developments of nanomaterials. Then how a material will be classified? So here typical images that will be picturized to understand the different levels of materials. So let me take a simple example of 1 to 2 mm of dimensions. So which will be relates to a pin head, safety pin head, and then 5 mm maximum it will be the ant, and then it will be comes to 200 mm. Then fly ash will be 10 to 20 micrometers, then 10 to 100 micrometers. Some of the mechanical micromechanical devices, MEMS devices that will be utilized. So pollen grains that will be picturized. These are all the things that will be in the range of 10 to 100 micrometers. Then red blood cells and white blood cells that will be in the range of 2 to 5 micrometers. So in similar way, then carbon nanotubes will be in the 1.3 nanometer diameters. So atoms of silicon will be at a tenth of nanometers. So these are all the different scales that will picturized here. So then what the unique material properties that can be featured by the nanomaterials. So the nanomaterials will have a higher surface area. Then some of the materials will exhibit a higher magnetism properties. Then it will have a very good quantum effects. So quantum is nothing but we are focusing in a minor, in a smaller way. So that will have a very good effect on that. Then the thermal and electrical conductivity, enhancing the thermal and electrical conductivity of a material. Then it exhibits enhanced mechanical properties. In some cases, it will be acts as a catalyst, and then it will in specific antimicrobial activity. So these are all some of the specific focus on the nanomaterials. Then common properties that be focused on the creation of functional nanomaterials or nanomaterials. So this will be general mechanical properties that will be supported to obtain the elevated tensile strength, highest elevated tensile strength. Then thermal properties, some of the physical properties, electrical properties, magnetic properties, then catalytic, chemical properties, and optical properties. So these are all some of the properties that can be help that can be aimed to having betterment over these properties, particularly with the addition of nanomaterials. Then classification of nanomaterials. So how a material will be classified, particularly a nanomaterials. So depends upon the structure, it will be categorized. Then depends upon the dimensions. Then depends upon the pore dimensions, and how it will be originated, how it will be nanomaterials will be made, then how it will have a toxicity. So depends upon these categories, the nanomaterials is been classified. So when I have been coming to a structural configuration, it will be broadly categorized into carbon-based, organic, inorganic, and composites. So carbon-based materials, the primary thing will be a carbon-based one. So in what form it will be? Either it may be in effluents, or it may be a graphene, or it may be carbon blacks, or it can be a carbon tubes, or it can be a carbon fibers. So it depends upon that, it will be, these are all categorized as carbon-based materials. So other thing, when you've been coming to organic, ferritin, micelles, liposomes, and dendrimer, these are all been material that will be considered in an organic way. Then inorganic, metal-based, metal oxides, then lipid-based, ceramic, and semiconductor-based. So these are all some of the inorganic. When you have been clubbing each and every one together, that will be relates to the composite nanomaterials. Then coming to dimensions. So if a material will have a 0 dimensions, then it will have a 1 dimension, 2 dimension, 3 dimensions. So based upon the dimensions, it will be categorized. And then pore dimensions. So if a material will have a pores in that, so porous material, so it depends upon the nature of porous, whether it will have the porosity have a dimensions. So if it will have a least minimum thing, then it will be microporous. Then intermediately it will be mesoporous, and then macroporous. It will have a large number of dimensions of pores. Then based on the origin, whether it may be an artificial one or it will be a natural one. So it depends upon that, it will be categorized. Then potential toxicity, how it will be. Then CMAR, and then biopersistent granule and fiber-like particles. These are all have been comes under this category. So according to the dimensions, we have been studied that 0, 1, and 2 dimension, 3 dimensions. So all the dimensions, all the nanoparticles, which will have a 1 to 100 nanometer range. For example, a quantum dots. So nano clusters, nanospheres. So it's a typical image that will be picturized here. This can be comes under your 0 dimensions. So though it will have a certain dimensions, it will be a very negligible range. So hence it will be comes under your 0 dimensions. So when you have been picturizing in 1 dimensions, so it will have a X and Y dimensions. So it will have in the range of 1 to 100 nanometers. So nano wires, nano rods, carbon nanotubes can be called as a 1-dimensional thing. Then 2 dimensions. So it will have a definite length and thickness. So which shows that it will have 2 dimension, which will be also in the range of 1 to 100 nanometers. So where nanofilms, graphene sheets, oxide sheets, Then layered nanomaterials. This can be categorized under 2-dimensional one. Then 3-dimensional one, which will have dimensions X, Y, and Z in a considerable range of nanometers, 1 to 100 nanometers, where dendrimers, bulk powders, graphites are being categorized under these 3 dimensions. So apart from these dimensions, 1 and 2 dimensions, some of the advanced properties, some of the morphologies of nanostructured materials, you can able to visualize that even though it will have a very thin, negligible amount of thickness, the nano zero-dimension particles will have a different morphology. You can able to visualize that there will be a core and shell, which will have 2 different properties of a materials, or a nanoparticle that will be encapsulated in a 0-dimension. So think it of how difficult it will be. Then composite nanoparticles. So these are all the things which will have a very negligible range of dimensions that can be categorized into 0 dimensions. In a similar way, you can able to visualize that these 0-dimension nanoparticles that will be sticked over or coated over the carbon nanotubes. So like that. Then another thing, coaxial nanowires. So 2 different materials that will be stacked in the coaxial way. So that will leads to a 1-dimensional thing. Then a composite nanowire, array of composite nanowires even at the 1 dimensions. Think it of these are all some of the advancements in the nanostructured material morphology. Then when you are coming to a 2-dimensional, a sheet of materials that will be made. In addition to that, these 0-dimension particles, nanoparticles will be embedded over the sheets in a very least negligible, least amount of thickness under a nano range. Then graphene-based composites under a different different dimensions. Then different morphological coatings, nano carbon plates that will be made here. Then nano belts. So in 3 dimensions, mesoporous, you can able to visualize that there is an electrode that will be stacked inside a hexagonal honeycomb structured thing. So then microporous composite electrode, a 3-dimensional object inside that the 0-dimension particulates will be stacked inside that. Then 3D electrodes, it will be in the lattice structured way. So these are some of the advancements in the nanostructured materials apart from the conventional 0, 1, and 2-dimensional, 3-dimensional way. Then some of the methods that will be utilized in the synthesis of nanomaterials. So there will be 2 different approach. One will be bottom up method, and another one will be top down method. So in the bottom down method, there will be 2 different categories. One will be chemical methods and another one will be biological methods. So mostly engineering, when you have been looking into engineering aspects, the chemical methods will be utilized in order to create functional or nanomaterials. Some of the methods that will be picturized here: Sol-Gel method, spinning method, soft and hard templating method, pyrolysis method, chemical vapor deposition method, then salt thermal and hydrothermal method, then reverse missile method. So these are all some of the methods that will be utilized under the chemical method process. When it comes to top-down method, there will be a thermal decomposition, mechanical alloying method, so laser ablation method, sputtering method, then arc discharge method, and then nanolithography method. These are all some of the methods that will be comes under the top-down method. So then what is a top-down approach and what is bottom-down approach? So top-down approach is nothing but if you can able to visualize this. This is a bulk material. So this will be splitted into fine particles. So that will be called it as a top-down approach. A higher particle size will be breaks into a finer particle size. That will be your top to down approach. That is a higher size to lower size. So that pictures the mechanical milling or laser ablation or sputtering or electro explosion method. Whereas in bottom approach method, we are going to made in an additive manner like that. So we are going to have a smaller particles will be get stuck together and it will be nucleated and it will be further developed in order to get a nanoparticles, nano range particles. So that will be called as a bottom up approach. So now we are going to discuss about some of the techniques that will be utilized to realize the nanoparticles. So one of the most familiar method in engineering will be your ball milling method. So this will be a top-down approach method where the particles that need to be converted into a nano level will be taken in a micron level. So micron level powders will be taken into a consideration and this will be put into a ball mill. So ball mill is nothing but it will have a rotating chambers. It will be called as a vails. So each vails will be the powders will be put into the vails, and in addition to that, balls will be added together. So why it was been rotated in this way? So due to this motion of rotation, the balls will be taken to the upward, then it will be forced to be downwards. So this will be created by the centrifugal force. So this movement of balls inside the cylinder will make the balls to get collide with one another. So during these collision between the balls, the particles that will be micron level particles that will be entrapped in between these balls will be get stuck in between, get stuck with the balls, and it will be gets hammered, and this made the material to get deformed. First initially it will be elastically deformed, and further get into contacts it will be elastically deformed, and further collision, during the collision it will be gets into splitted into particles. That then this way these particles will be made into a finer particles. So this will be a small video that will have insights on how the ball milling will be works. Hope this video will give an insights on the better insight on the how the particle will be subjected to a centrifugal motion during the ball milling process. So now the next one will be the lithography. So this will be utilized in order to create a nanostructures. So what are the different kinds of nanostructures that can be possible through the lithography will be picturized here. There will be a suspended structures. So you can able to visualize that there will be two supporting structures. In between there will be a structured material will be made. So next one will be the 3D structures like Egyptian model. So it can be made. Not only these kind of structures, any kind of structures which will be based upon the requirements, it can be made with this method. Then hybrid structures. So combination of two different structures that can be made. So these are all some of the structures that can be obtained with the help of a lithography, where the lithography in which the material will be focused with the help of an ion beam, and this will be implanted over a substrate. So this can be obtained. This can be obtained with the help of a mask. So that may be made with the help of agents. So this will help you to get the required structure with the help of a mask. So So this will be a video that will shows how a lithography can helps you to make the structured materials.
This short video will teach you the basics of electron beam lithography. Lithography is a word that comes from ancient Greek, meaning printing with stones. With this technique, a stamp is made by carving a pattern into a stone. The stone is then coated in ink and pressed onto a substrate, such as paper. Similar methods are used when making small microscale devices, where a pattern needs to be made repeatedly on wafers. The two methods used are called electron beam lithography and photolithography. EBL uses electrons to print, while photolithography uses light. Both methods use an organic material called a resist, which is sensitive either to electrons or light, depending on the material used. A thin coat of this resist is applied to the substrate. In photolithography, the resist is exposed to light through a patterned mask that has been transferred onto the substrate. Wherever the mask allows light to reach the resist, a chemical reaction occurs, in which large resist molecules are broken down into smaller molecules. After exposure, the next step is called developing. The area of the resist that has been exposed to light is removed by immersing the wafer in an organic solvent. The solvent dissolves only the small molecules that were produced during the exposure to light. Finally, the pattern is transferred onto the substrate using one of two available methods. Method 1 is etching, in which substrate is chemically removed from the pattern area that is not coated in resist. After etching, the remaining resist is removed, revealing the pattern etched into the substrate surface. Method 2 is the lift-off technique, in which a metal layer is deposited over the whole of the wafer. The resist is then removed, taking the metal layer with it. The only area that now has a metal coating is the desired pattern, where the resist had previously been removed in the developing step. Electron beam lithography uses the same process scheme, but a focused electron beam is used for exposure. The beam is accurately directed to positions on the wafer to form the pattern. The electron beam exposes the pattern dot by dot and line by line, which can be more time-consuming than photolithography. However, it is a more flexible system and does not require expensive masks. The focused electron beam also allows feature sizes below 10 nanometers to be generated. Common applications for EBL are rapid prototyping, small batch production, where electron beam lithography and photolithography are used in conjunction, as well as the fabrication of masks and imprint templates.
Hope you can able to understand that how a lithography process will be made. So two different processes will be explained here. One will be your electron beam and another one will be your photolithography. So both the things we can be utilized to create a nanostructures. But only thing is it will highly relies on how accurate this will be, and the mask that will be required will be different when you have been focusing on photolithography and electron beam lithography. But when you have been moving with the electron beam lithography, you can have a more precise and accurate structures compared to photolithography. Then electron spinning. So this will be another technique or method that will be utilized to synthesize the nanoparticles. Particularly, majorly, this will be utilized to create a nanofibers. So in this, there will be a syringe type system that will be helps to focus the different materials in which what kind of nanomaterials we need to create. So majorly, it will have a coaxial nozzles. So these coaxial nozzles, through these coaxial nozzles, the material that needs to be synthesized has to be pumped in, and at this tip, so there will be a high voltage supply will be given to this tip. So due to this high voltage, the particle that will be impinged over that will be gets polarized and it will be collected and over a substrate. So this collected material will be in the form of nanofibers. So generally, it will have two or three type of materials can be included in that. So one will be precursor solution that will be to have a better formation of nanofibers. So some of the nanofibers that will be made through this electrospinning technology will be pictured here. So you can able to visualize the thin nanofibers and in the individual nanofibers which will have a nanoparticle which in the range of highly it can be equal to 50 to 100 nanometers in thickness. So this video will give an insights on how a electrospinning process will be works. So hope you have been visualized that how a material will be pumped from the syringe and it will be moved to a cone. Then it will be made into a fibers and then it will be gets into a collector in the collector plate. So then next one will be your sputtering method. So in this sputtering method, generally the substrate will be collected and the material that need to be coated will be kept over the substrate. So in addition to that, the argon gas will be purged into that. So this will be flows over that. So this made the materials to gets to be coated over the target material. So it depends upon the power supply that will be focused on that. So these target materials will be focuses this argon sputtering. So this will make the ejection of sputtered particles with the AR plus, and that this ideally gets the formation of thin film over these heating substrate. So in such a way that the particle, the nanoparticles will be gets to be coated over the substrate. So this will be the thing sputtering method. So the video will give an insight on how a sputtering will be happens. So hope you will get a better insight on how sputtering will be works, and this will help you to create or synthesize thin nanofilms or nanostructures, nanotextures that can be obtained with it. So next, another one will be your arc discharge method. So this is the method which will be very simple enough, as similar to your electric arc that will be generated in between two different electrodes, positive and negative terminals, under these two positive and negative terminals. So in this case, there will be two terminals, two rods that will be anode and cathode. So there will be a chamber inside that. The gases will be flows inside that, and gas will be flows out. So when a power supply will be given to that, then in such at the time, the particles that will be followed with that, the atoms will be gets into formed during these arc in between the high electric supply. So due to this, the particles will be gets formed, and we can able to obtain the nanoparticles. Mostly the carbon nanoparticles will be made with this kind of thing. So how a particle will be made? First, initially the organ will be argon and nitrogen or helium that will be passed into that. So first, initially the quenching of will be happens. So in this case, there will be the precursor, that is the formation of bonding between these carbon and carbon atoms will be happen. Then further, the growth of the atoms will be accomplished. Then it will be leads to the agglomeration. So again, if you have been taking to the nanostructure wires in such a case, so carbon to carbon or carbon to nitrogen, so that can be obtained in a similar way of formation of precursors or further growth of this. Then in next level, you can able to identify with the help of carbon to carbon. So in the form of thin sheets that can be identified. So whereas in this case, the first condition, the organ will be utilized. In the second case, nitrogen. Third case, H2 hydrogen will be utilized in this case to obtain the three different conditions of nanomaterials. Then chemical vapor deposition. So this is a common technique that will be utilized in this case. So there will be a substrate material that will be subjected to heat. Then it will be the atom that will be pumped into that. So due to this attraction towards the particles, the chemicals will be gets deposited into the target substrate, and we can able to obtain the nano coatings or nano textures through the chemical vapor deposition. Then another method will be your sol gel method. In this, first the solution precursors will be made. Then it will be form a sol, and further the sol will be put into the condensation. There we will get a gel process. So then this gel will be put into a evaporation of gels. Then the particle that will be suspended over this will be gets separated, and then it will be put into subjected to a heat treatment to get a coarser materials. So this will be one case. Another one will be the salts will be subjected to a spin coating or dip coating, where these gels will be segregated in the form of layers over a substrates. Then further the heat treatment will make the gels to get a dense way. So this will in this way the nanoparticles will be obtained through the sol gel methods. So till now we have been discussed about some of the different techniques that will be adopted to identify the or to synthesize the nanomaterials. So now why these nanomaterials has to be created, or a nano powders or a powders that will be required, particularly when you have been discussing to additive manufacturing. So when you have been focusing to the additive manufacturing, some of the basic characterization of powders that need to be addressed. In addition to this characterization, we have been move on to some other scanning electron microscopy or transition electron microscopy that can be put into that. But some of the primary characterization that will be required for powders. So will be picturized here. First one will be the density of the particles, then particle size distribution, then size of the particles, then a particle morphology, and what about the crystalline phases that will be exhibits, then particle elemental composition, and then particle surface molecular, how it will be. So these are all some of the things that need to be considered when you have been moving to an additive manufacturing. So since for powder-based additive manufacturing system, the metal powders will be the primary source of material. So in such case, so without having in-depth knowledge on the characterization of powders, so it cannot be straight away, it can be put into additive manufacturing. So it depends upon these parameters, these factors, the additive manufacturing of a component will result in a different exhibits a different properties or different natures. So density of particles. Before moving to that density of particles, how a particle density will be identified? Okay, let me just discuss some of the things. Density, when you have been coming to a density of powders, there will be different kinds of density. One will be your apparent density and another one will be your tap density. So these are the density. What is apparent density and what is tap density? So why we need to consider these apparent density and tap density? So apparent density is nothing but a density when it will be obtained as it is, when it will be poured to a certain volume of material. Generally, this can be identified with the Hall flow meters. So Hall flow meter, generally there will be a specified volume of jar or a beaker container. In that it will be, the powders will be poured over that. So now the poured powders will be filled off over the container. Then it will be subjected to a measurements and how much it weighs. That will be considered as a mass. Then the volume that will be occupied by the powder, that will be taken and it will be put into the calculation, and we can able to identify what is the density that the powders will have. So that will be called as an apparent density. And then a tap density. So what is tap density? So even after we have been poured into that, then the powder will be gets tapped on the sides. 1 tap, 2 tap, 3 tap, and number of taps will be increased. So even after a subsequent taps at regular interval of taps, so it will be put into a measurements and it will be identified what is the volume. Now the volume of material that will be observed in the apparent density calculation will be different. Some amount of volume will be gets compressed and the volume of that powder will be gets reduced, whereas the mass won't get changed. So in such a case, there will be a change in the density. So this will be called as a tap density. So when coming to density of particles, why we need to understand these densities? Then depends upon the density. If the material will have a higher density, so when it will be subjected to additive manufacturing, when it will be poured over a layers, so these particles will be have a higher density. It will be gets settled over the respective position when it will be forced, or it will be poured over a layer during the powder bed manufacturing. So if the material doesn't have a required density, in such a case, what it will happen? So it won't get filled off at a uniform way, and it will have a in between there will be a particle gap will be there that will result into the production of porosity, and it will have a very least amount of packing density, which is nothing but the entire surface that what we need to be packed off, filled off, will not be properly filled off. So that will result in the reduction of package density. That will think. So in what way this will affect? So that will result in the generation of porosity in the part what you are going to make powder sintered materials, powder additive material. And then it will affect the green density, which is nothing but it won't have a proper consolidation between the particle together when it will be subjected to a particle sintering. So these are all the thing that will affect in the additive manufacturing component. Then next one will be the particle size distribution. So particle size, how a particle size will be analyzed? Generally, two different methods, conventional methods and advanced methods. So conventional method will be a sieve analysis will be made. In that, it will have stacks of meshes will be made. So from higher levels to lower level, it will be stacked off in different mesh size, different particle size. When a specific quantity of powder, generally 100-gram quantity of powder will be taken and it will be poured on the top sieve. Then it will be put into a vibration shaker, and these vibration will make the powders to be filtered off in each subsequent sieves. And finally, after a certain time period, the particle that will be relates to a particular mesh size will be gets trapped in each sieves, and then that will be collected together, and each sieve will be quantified how much it will be, and then it will be picturized and it will be categorized how much amount of percentage of materials will be collected in each sieves. So if it has been plotted together, so you can able to obtain a curve that will fits what is the particle size and what is the quantity of powder that will be obtained in each particle that will be picturized with this particle distribution curve. This will be a conventional method. Now advanced particle size analyzer will be there. Even a laser-based particle size analyzer there will be there. A pinch of particle that will be suspended over a fluid, and that will be put into analysis. That will help you to identify the particle size, how the particles will be distributed in different sizes. That can be identified, and that will help you to identify the average particle size of the powders. So in what way this will affect? So why we need to understand the particle size? So if a particle will have a mixture of all the sizes, in such a case, when you have been placing a particle over spreads over a surface during the powder bed fusion sintering. So the particle, if it have a mixture of particle, then each particles will be gets collided, mixed together, and entirely it will be fills over all the area. So it will have a better mixing of particles, and it will be uniformly packed over that. Thus it will helps you to have a better package density. If it has been too fine, so it cannot be able to have a proper spreading of powders over that. And then if it is too coarse, if the particle size will be very much higher, so there will be a space inter particle space will be higher. That will result into the rough surface, or in between space between them results in the formation of porosity. So thus a better composition of mixture of powders will be required to have a better package density, and that will result into the formation of layers, subsequent sintered layer with uniform density and surface textures. Then particle size. So definitely a particle size will have a impact over the additive manufacturing. Generally, people have been looking into a particle size which will have larger particles and smaller particles. Generally, the smaller particles will have a higher surface area, which will leads to a very good bonding between each particles. Thus it will helps you to have a better bonding between the particles. But whereas when you'll be looking into the flowability of particles, if the particle size will be higher, it won't flow in a proper way, that it reduces the flowability. So another way will be the flowability. When you have been that will be also measured with the help of a Hall flow meter. And then if the particles will be larger in size, So if the particle will be larger, that will helps you to have a better flowability. But we could not able to identify, obtain a higher package density, which is nothing but it not be spreads uniformly over the area of the where we need to spread some. So this will impact in additive manufacturing that if the particle will have a fine powders, that is, it will have a smaller particles, it will help you to obtain a higher package density and better resolution, and it will have a risk of oxidation and poor flow in some cases. When you have been moving to coarse powders, so lower packing density, it won't be spreads off uniformly, and it will result in the formation of higher porosity in the additive made parts. Then another thing will be particle morphology. So how a particle shape will be, how it will be. Generally, different kinds of particle shape. Generally, it will be in the form of flakes. It will be in the form of spherical. It will be in the random. Then it will be in the form of wires. So different kinds of particle morphologies will be there. When coming to additive manufacturing, preferably they have been focusing on the spherical kind of particles. And why not irregular particles? So spherical particles will be flows very easily, and it will be gets packing packed spreads over the surface uniformly. So that's why people have been preferring spherical particles, and it will have a uniform interparticle spacing between the particles that will help you to have a better uniform surface texture to obtain a surface roughness. Whereas if it is have a irregular particle morphology, then it will help you results in the formation of interlocks, or it will have a results in the trap porosities. So it will leads to variations in the density at different places. So this will results in the additive components that will have defect samples, or the samples will not have a uniform surface roughness. And these are the things. Then particle crystalline phase. So how a crystalline phase is? For example, if you take a titanium, it will have two different phases. Even though it will be a titanium, the material will have exhibits, a pure material will exhibits at two different phases. Depends upon the temperature that will be put into subject. So for example, if it being subjected to a temperature below 882 degrees Celsius, then it will be exhibits alpha structure. So beyond the temperature, it will the alpha will be transformed to a beta phase. So at different phases, it will have a different density, slight difference that it will be 4.46 for alpha, and it will have been more than 4.5 for beta. So these difference in phases will leads to a different densities and melting behavior that will be affects the property of additive sintered components, and this will be results in the change in transformation of phases that will leads to a shrinkage of material or a formation of porosity during the additive manufacturing. Thus, it will helps that will impact the melting. So there won't be a uniform of melting of material that will be happened during this change in phases. One thing, then that will result in the densification. So it won't be have a proper thing. So there will be a shrinkage will be happens during this change in behavior. So that will result in the porosity formation. Then in terms, it will affect the metallurgical behavior. Then particle elemental composition. So particle elemental composition is nothing but, though it will be a pure material, when it will be subjected to different conditions, environmental conditions, or different temperatures, even though it will be a pure material, the surface, the external surface may be subjected to an oxidation. So in such case, there will be a different kinds of phases that may be formed over the surface. So that this will be results in the affects the melting efficiency, the material cannot be properly melted. The surface oxides that will be formed over the particles will make the material to melt a little bit slower. So then in such a case, it won't be melt properly. So this will result in the density of material that will be consolidatedly. We cannot able to have a higher density materials. So also it will be leads to the formation of defects. In some cases, it leads to a cracking due to hot cracking due to thermal gradients. So the next one will be your particle surface molecules. So this will be leads to some contaminants or oxides that will be formed during this. Particularly when you have been focusing on the laser or electron beam based welding, the melting will be differs. Then the absorption of energy, laser beams will be different. That leads to the defect materials. So some of these standards that need to be adopted when need to be subjected to a characterization of powders. So as we have discussed, apparent density, so it will be ASTM B212. Then flow rate of metal powders using hard flow meter. So these are all some of the standards that need to be adopted when you have been characterizing the powders. Then challenges in these nanomaterials. One major thing will be the presence of defects in the nanomaterials. So that will affect the performance of your material, additive manufactured material, particularly metallurgical behavior. In terms, it will affect the functional property of your nanomaterials. Then next one, synthesis of nanomaterials is a big challenge, and it will be a cost incurred process. So it needs a sophisticated instrumentation to produce such a kind of things. That is a major problem towards the nanomaterial synthesis. And then next one will be the agglomeration of nanoparticles. As the particles will be at a nano level, generally the agglomeration of nanoparticles will be happens in this case. And then synthesis and stability of 2D ultra thin materials. Since as it is a very thin structured materials, so it will be quite little bit difficult when compared to a powder particles. And then the stability of these ultra thin materials. So these are all some of the challenges that will be faced by the peoples. So this will show some of the applications where it will be put into the nanomaterials. So hope plenty of applications in diverse domain will be have. So generally how most kind of materials that will be graphene, carbon nanotubes, mixins. So this will be utilized. The implementation or utilization of nanomaterials will greatly supported in the energy sectors in terms of creation of supercapacitors, and then developments of batteries that will helps you to reduce the size of batteries. Then it will be helps in the reduction of carbon emissions and development of fuel cells, then drug delivery systems. So some of the applications related to that. So then some of the specific applications where the nanomaterials will be utilized. So AGNWs, that is silver nanowires, then copper nanowires will be utilized in the development of solar cells. That will be helps to the development of electrical energies. Then lithium, sodium, potassium, that will be utilized in the supercapacitors. Then carbon nanotubes and transition metal oxides, nanosized composite materials that will be utilized in the lithium ion batteries. That will help you to enhance the energy level of the batteries, energy capacity of the battery. Then gold and iron based nanoparticle that will be helps to diagnose the cancer and tumors. So then gold particles, silicon particles, then carbon nanotubes, and then it will be utilized in the drug delivery system, then cancer therapy, then medical industries. So these are some of the specific application materials, the nanomaterials that will be utilized in the specific applications. Then coming to food industry, titanium dioxide that will be utilized. Then silicon oxide, zinc oxide, copper oxide, magnesium nanoparticles. Some of the particles that will be utilized in the agricultural industry as a fertilizers. Then antibacterial materials. Then it will be high sensitivity sensors. So in all the domains, it will have in displays, carbon nanotubes it will be utilized in the displays to create a pixel size level displays in constructions, cutting tool materials. So then energy sectors, textiles. So in different domains, the nanomaterials will be utilized in order to enhance the material properties. So this is about the presentation. So thank you for your patient listening. So if you have any doubts or queries. So if there is any doubts, you can ask now, or you can put it in chat box.
Participants, the session open to the participants. If you have any queries.
Yes, sir. Yes, sir. Thank you very much for your presentation, Professor. It was really very informative. From zero dimension to the current applications, you have explained very nicely. On behalf of participants, I would like to say thank you for your presentation.
Thank you, Professor.
I have a little bit doubt. It's not doubt of clarification.
Yes, Professor.
Is there any difference between surface morphology with respect to surface structure?
Yes, Professor. Of course, surface morphology is entirely different. Surface texture is different. For example, let me take a ball. Then let me take a disc. So two different things. This will be call it as a surface morphology. How it seems. So ball will have a different morphology. That is how it been visualized. This will be the surface morphology difference. For example, let me take a ball and disc. So both the things will be have a texture. For example, if I want to create a circular texture over that. For example, in ball, we can have a different colors. நிறைய colors இருக்குல்ல Professor. கலர் அடிச்சிருப்பாங்க. So இப்போ அந்த கலர்ஸ் எல்லாம் பாத்தீங்கன்னா different colors டெக்ஸ்சர்னு சொல்லலாம் நம்ம. டிஸ்க்லயும் அதே மாதிரி டிஃபரெண்ட் டெக்ஸ்சர் சர்க்கிளாவே டெக்ஸ்சர்ஸ் கிரியேட் பண்ண முடியும். ஸோ இப்போ என்னன்னா மார்ஃபாலஜினா அது எப்படி இருக்குன்னு சொல்ல போறோம். டெக்ஸ்சர்ங்கிறது அந்த சர்ஃபேஸ்ல we have been creating some required geometries or required way of modification.
Like that.
Yes, Professor.
Okay, thank you so much, Professor. Thank you. Thank you,
Professor.
Thank you, sir.
Gopi sir.
Hello.
Sir.
Can you hear me now?
Yes, sir.
Yes, sir. Good evening, sir. There was some. Okay, good. How are you, sir?
Sir, good evening, sir.
Yeah, good evening, sir. Good evening. Yeah.
Just 2 minutes, I will start the session. Just 2 minutes.
Yeah. No problem.
Sir, Palichami, sir.
Sir, children, sir. Yes, sir, please, sir.
So if there is no queries,
Okay, sir.
I will just leave the session, sir.
Shall we
Just
close
a
the
minute,
session,
just a minute,
sir? Adhi, sir?
Sorry, sir. Gopi, sir.
Sir?
Just close this session and start the second session, sir.
Okay, okay, sir.
Yes, sir. Thank you to all. Thank you, Professor.
Thank you, sir. Thank you very much. Very good.
On behalf of Department of Mechanical Engineering from Adhi College of Engineering, I sincerely thanks Dr. S. Satish, Assistant Professor, MIT Campus, Anna University, Chennai, for delivering insightful and engaging session. Thank you for your valuable presentation. Thank you, sir. The next section will be started in few minutes. Sir, Panichami, sir, shall we start the session, sir?
Yes, sir. We can start. Just a minute. Now we can start. No problem.
Okay, okay.
Green circle. Good evening, participants. Hope the previous session was about design, fabrication, character appreciation. Session will be handled by Professor Shiva Shankar, and he's a professor from Qasim University, Saudi Arabia. Session, let me introduce Professor Shankar. He's a professor of mechanical engineering at Qasim University, Saudi Arabia. He earned his PhD from production engineering from National Institute of Technology, India, securing a perfect CGPA of 10 out of 10. With over 20 years of teaching and research experience, he has specialized in nanocomposites, powder technology, welding, additive manufacturing, and suitable and sustainable materials. He has authored about 150 international journals, books, and book chapters, contributing significantly to material science research and etc. Dr. Shivashankaran has successfully led 20 plus funded projects and established advanced research laboratories in manufacturing and materials engineering. He is patent holder in high entropy composites and has received global recognition, including a bronze medal at the Geneva Innovation Exhibition. A passionate academic, he actively guides students and researchers towards innovation and entrepreneurship. His work continues to make a remarkable impact in advanced materials manufacturing and engineering education worldwide. There are many things to say. Before that, let me conclude. And now I hand over the session to Dr. Shivashankar. Professor, you can please handle the session, Professor.
Yeah. Thank you, sir. Thank you very much for your nice introduction, sir. Good evening to everyone. I hope that everything is fine with you. And first of all, I would like to thank the organizer, Dr. D. Palaniswamy, who has given an opportunity. And also, I would like to thank the Department of Mechanical Engineering, head of the department, and all the principal of Adhi College of Engineering. Welcome to all the participants and all the experts who have delivered before me. Right. So, can you able to see my screen, sir, now?
Yes, sir.
Can you all see my screen?
Yes, sir.
Yes, yes, yes.
Yeah. Okay. Right. Okay. Good. Right. So today I would like to share about my expertise, my experience related to design, fabrications, characterizations, and mechanical performance of thin wall metallic component. It can be produced via wire or additive manufacturing. And everyone know that nowadays the additive manufacturing is completely changing the advanced manufacturing sectors actually. Why? Because whatever the complicated product which you want to produce, either in medical field or a mechanical field, any automotive component, aircraft component, we can easily produce via additive manufacturing. Actually, it is not a new technology. Olden days, we used the additive manufacturing concept to make the prototype actually. But now, once the patent has been
over. So people are using that their invented technology. That's what the things. Of course, there are many additive manufacturing technology. So wire arc additive manufacturing can give us a lot of benefits. It is a cost-effective technique, and moreover, the deposition rate will be very high. And any large component, very thin wall and large component, whenever you want to make it, wire arc additive manufacturing is the best choice actually. For example, in a hull or any propeller, turbine propeller, something, any propeller, something damaged, we can replace in the particular part only. It is not necessary to replace complete propeller. So that is the benefit of this wire arc additive manufacturing. So, and also we know very well most of the pressure vessels, okay, and the aircraft component, most of the product made from thin wall cross sections. Why? So we need to reduce the weight of the component. That's why thin wall cross section can be used. So for which wire arc additive manufacturing will play major roles. So we'll discuss one by one. So these are my presentation's content. So we will discuss about introduction to additive manufacturing processes and what are the basic types of additive manufacturing. I will we will discuss just maybe 10 to 15 minutes just for recalling the things. And then we will discuss about application of additive manufacturing. Then what are the advantages and disadvantages of the additive manufacturing. Then we will focus on wire arc additive manufacturing. Then what are the classification of VAM technique. Then when we want to develop the metallic thin wall cross sections, the selection of materials and some challenges are to be accounted actually. So what are the challenges to be noted? We will discuss on it. Then common defects. Of course, even though the VAM technique can be used for thin wall cross sections and large size component, there are some defects usually getting formed. We will there are some solutions that we will discuss about what are the common defects which usually observed in the VAM product, and what are the post-processing technique we have to use it in order to improve the surface quality. We have to do some post-processing treatment. So these are the overall way of my presentation's content, right? So, and as you know, we are all very well, additive manufacturing is nothing but a 3D printing concept. So here the product usually build layer by layer. Here the product usually build layer by layer. So each machines will do the operation based on this concept. So only thing we have to, whatever the component we want to manufacture it, we have to design it in the AutoCAD software, or we can, any complicated product, we can scan the files. So and then we can send the CAD file to the machines before we have to convert into NC codes, and then NC code will be sent to the corresponding 3D printing machines. Then it starts to the printing. So according to the type of printing machines, it starts to working on it. That is the basic things. Among the additive manufacturing techniques, VAM is the attractive one. Okay, why? Because high deposition rate, and it is a cost-effective technique, and scalability. That is these are the major benefit we can obtain from the wire arc additive manufacturing sections, technology. And one more point, thin wall metallic structures. So it is very important. As I told you before, most of the aerospace component, automotive component, energy sector, biomedical field, we want to reduce the weight of the system. Then only we can improve the performance of the particular product or particular systems. So for which thin wall metallic structure will play a major roles. As we discussed now, additive manufacturing. So it's nothing but it's that means through the additive manufacturing concept, we can build the product. We can build the product layer by layer. Only we have to send the digital file to the 3D printing machines, and then it can start the building of the component. Okay, right. Usually, as engineers, so we should know the difference between the additive manufacturing as well as the conventional manufacturing technique. And you know, additive manufacturing is a bottom-up approach, starting from like a building of the construction of the buildings. Okay, whereas conventional machining technique usually will follow top-down approach, or we can call subtractive concept. So from the product, we have to remove the unwanted materials. That is what the conventional manufacturing technique. So for which we need to use some machine tools, we need some lot of rolling machines, forging machines. Okay, and then we have to prepare some mold, there are many things we need. Okay, a lot of resources are to be used in the case of conventional manufacturing processes, but in the case of 3D printing, not like that. Of course, we can, once we done the printing of the component, we can do some heat treatment, some post-processing technique only we have to use it. Apart from this, that one, we can eliminate most of the resources what we are spending in the conventional manufacturing technique. Right, how does additive manufacturing work? So I think you are all basic things. So of course, whatever the physical product we want to build it, we have to make a drawings, either CAD model, or suppose in the case of medical field. So whenever they want to build some implant parts, like for example, human hull or something, it's a highly complicated product. We cannot design it by our own. And moreover, we have to do some customized based product. So for which the complicated product we cannot design using the CAD software, but rather we can do the scanning. So once we do the scanning, we can get the CAD data from the scanner. Then the CAD file will be converted into the NC codes. Then it can be sent to the machines for building the product. Right. So in the case of additive manufacturing, the raw material, so depends upon the type of machine. Material will be in the form of powder forms, or liquid forms, or gel forms, okay, or filament forms. So there are different types of printers. We will do some overall view about this technology. And nowadays, one more thing is 4D printing is also coming. And you know, 4D printing is also one of the best one. Actually, whatever the performance we are expecting from the component, in the 3D printing itself, we can program it, we can build it in the 3D printing itself. Then when it exposed to the atmospheric condition, when it exposed to the some heat, some environmental conditions, accordingly the product will start to do its performances. Okay, that is what the 4D printing. That means after printing, so that product will change the shape. Okay, so that is what the people are calling it as a 4D printing. People are doing a lot of research on this area. So based on the heat, water, or light, or wind, electricity, so the product will be will change its shape actually. So anyway, we cannot apply for all the materials. For example, shape memory alloy, some smart materials, self-healing materials. We can apply this 4D concept. Okay, so that means whenever the 4D component exposed to the some atmospheric conditions, it can elongate, bend, wrinkle, fold, and twist, so that we can expect a good performance from the particular product. For example, any structural applications, if there is any crack appear in the smart material, starts to identify by itself, then starts to expand it, it starts to join it. So that is the concept of the 4D printing. Right. So we will quickly all the 5 additive manufacturing processes. First one is binder jet. Okay, binder jet is also one of the powder metallurgy based 3D printing technique. So usually there are loose powder has to be spreaded over the bed. Then there is a liquid resin will be there, liquid binder will be there. The printer head, will suck or will absorb in the corresponding binder in both X, Y, and Z axis. Then it will spray on the particular area where we want to build the component. Then the roller will spread another layer of the powder, and then again the printer head will try to absorb or suck the liquid binder. Then it will be spread around it. So like that, so layer by layer we can build the the product. Okay, that is what the concept of the binder jetting. So under this concept, there are many printer: furon binder, silicate binder, phenolic binder, aqueous based binder. So all these binder are working. These printers are working based on the binder jetting technique. Okay, I will play some videos later. Then there is a second one is material jetting. So here droplets of liquid material will be spread around. Liquid material will be sprayed on the particular bed. Then there is a resin, light rays will try to cure the product. So here the material jetting build the objects one droplet at a time. Then the printer head can able to cure the product, and we can make the layer. Then another layer by layer we can able to print the component. It's not like a complicated. It is like a inkjet printer. So whatever we are using in the home, it is look like inkjet printer, but it can able to jet spray the materials. That is the plus point of the material jettings. Okay, right. So most of the polyjet printers, nanoparticle jettings, drop on demand, all are examples of material jetting printer belongs to this concept. Then directed energy deposition. This is the recent ones. So even for VAM and even for laser-based system, electron beam-based system, plasma based systems. So we can also build the product layer by layer, which is called directed energy deposition. Here there will be focused energy will be there. There will be focused energy will be there. That focused energy will produce a lot of heat. Okay. So by which if we introduce any filler material like any metallic wire or powder, okay, it can able to melt and we can able to deposit the layer. So this is what the concept of directed energy depositions. So laser, through laser also we can get the we can build the product through plasma or constructive arc and high ionized gas. We can able to do the printing, and also we can do electron beam also. It can able to give the energy as a power. Okay, then by which we can able to print the system. That is what directed energy deposition. You can see the laser beam is coming here. Then powder flow will be coming here. Spherical powder will be coming here. So whenever that's coming here, it starts to melt and it will be deposited. This is what direct energy depositions. When compared to the fused deposition modeling, this printer will give you a lot of benefits. Okay, so that's what the things. Anyway, here the multi-axis robotic arm will be there where we can send the raw materials. Okay, so that's what. And some examples. For example, laser engineering mesh formations, directional light productions, direct metal depositions, 3D laser coating. All these concepts are working based on the directed energy depositions. Then material extrusions. This is the old one. I think everyone is know very well regarding this is what fused filament deposition technique. So that means here the raw material will be in the form of filament. It has to be sent to the heated nozzles. Then the heated nozzle will absorb, will suck the wire and will start to melt, and then it can able to deposit the bed where we can able to build the component layer by layer. This is what material extrusions will be involved in this concept. So most of the, for example, initially people invented only single filament, single nozzle based 3D printer, then twin nozzles, and even nowadays composite filament fabrication, composite printer is also coming, where you can print both matrix and fiber materials, and by which we can develop the composite product. This is what material extrusion based printer, composite filament fabrications, fused filament fabrications, fused deposition modeling, all are under the categories of material extrusion based 3D printing concept. Then powder bed fusions. Okay, powder bed fusions. This is also one of the important. Most of the critical component mostly made from a laser powder bed or any powder bed fusion technique. Why? Because we can get net shape, okay, and we can get good quality product. For example, VAM. Of course, it can be used only for a large and very big product, but we cannot achieve the good quality of the component. Okay, so for which we need to do some other machining. Whereas in the powder bed fusion technique, we can exactly produce the high quality component. Accuracy. Apart from that one, we can have homogeneous structure. Okay, the weight will be distributed uniformly. So homogeneous structure can be produced through the powder bed fusion technique. Okay, so by which we can able to get extraordinary mechanical property. That is the plus point of the powder bed fusion technique. Only thing, the cost is expensive. Okay, cost will be the expensive, and there will be a lot of powder will be wasted on it. This is what the powder bed fusions, and the working of this concept. Usually the bed will be upper positions. So there is a hopper. There will be roller. It will spread the powder one layer. There is a source from the laser. So it can send, according to our drawing, it will send the laser source, and wherever there is a pot drawing is there, pot is there, it can able to pass the laser, and the pot with the particular area will be sintered, will be bonded. then another layer, then so in the bed in meantime it will go down. So like that, layer by layer, we can able to print the component. So through this concept, there is a direct metal laser melting, direct metal laser sintering, electron beam melting, selective laser sintering, selective heating sintering. All these are under categories of powder bed fusion technique. Okay. Then one more point, one more point is sheet metal. Nowadays we can able to stack very thin metallic sheets, and then we can by applying the high pressure and high temperature, we can able to do the shapes. That is what sheet laminations. So here the raw material will be in the form of paper or plastic forms or metal foil forms. We have to spread it. There is a roller we can able to spread it. Then there is a sonar ultrasonic head will be there. It can able to send the with pressure and send the heat. So by which we can able to join the particular area. Okay. The meantime, once the product is done, then there is some cutter will be there. We can able to cut the excess materials. So one layer will be there. Then again, second full layer of they will spread the sheets. Again, the sonar rod. It will come. It will apply the force and pressure. Then wherever the parts are to be glued, it will be joined. Then there is a cutter will come. Will try to cut the unwanted area. This is what the sheet lamination technique. So example, ultrasonic additive manufacturing, selective deposit layer, laminate object manufacturing. All the examples of through this technique. Then last one is polymerizations, VAT polymerizations. And this is here a liquid polymer. Okay. So whichever the polymer can able to expose to the ultraviolet, it can be used as raw materials. So by which also we can able to print the parts. Okay. So there is a VAT resin tank will be there. Initially the head will be, that means the bed will be upper positions. And there is a light source, UV light source will be there. So according to the drawing, so the light source will be hit on the particular area. Then it will go down. Then next layer of liquid polymer resin will be coming up. Then again it will be we have to send that means the laser system will be send the UV rays, and the particular wherever the UV rays are exposing on the resins, it will be cured immediately. The part will be solid. Okay, so that's what VAT polymerization technique. So what are the benefit means? We can get exact precise components through the polymerization technique. Best example, stereolithography, digital light processing, liquid crystal display. All these printers will work based on the polymerization concept. Okay, so the main objective, the main advantage of this printer is any kind of complicated product we can able to produce with high quality. So that is what the plus point of this technique. So I will show you 5 minutes, just one important videos. So you can watch on it. Then we will continue about VAM technique. So they are explaining the different stages of the system actually. So there are short videos. Only I will play 2 to 3 videos just for. Right. So I hope you can understand the thin wall fabrication of thin wall structure using the direct energy deposition technique. Right. So there are many videos. I think you might have, watched or you might have learned in the previous sessions. Let's focus on our topic. Right. So, and you know very well, the applications of additive manufacturing process are very vast. All the aerospace component, automotive component, healthcare, and energy sector, consumer product. People are focusing on this area to develop a lot of real-time application, real-time components. Right. What are the advantages we can get from the AIM process? Actually, the best one is design freedom. So whatever the, for example, conventional manufacturing technique, based on the facilities available, based on the machine tool available, we have to design. Okay, there is no much system freedom. But here, whatever the product we want to design it, we can able to print it. That is the plus point of the AIM process. Design freedoms. We can build any geometry possible in the CAD, and it can able to enable the complex shape impossible with the traditional methods. That is the plus point of the AIM process. So most of the aerospace components, bioprinted scaffold, so are examples of AIM process. Okay, right. Then high customizations, and moreover, lightweight component can be easily produced via 3D printing technique. So we can do optimize the geometry with less materials. Whereas, for example, the conventional manufacturing technique, lot of wastage will be there. So scrap will be there. So which can be completely eliminated by means of the AIM processes. And further, low maintenance productions. Okay, that means what? Whenever there is an order, we can start the productions. Okay, so for example, old and manufacturing industries, so they usually produce the product in number of more quantities, and they have to store in a particular places. There will be a cost for inventory, and many things will be there. So and then degradation will be there. Okay, so all these things we can completely eliminate by means of the AIM technique. That's what the some advantages on-demand manufacturing. Then we can produce sustainable and less wasteful product. So these are the main advantages of the AIM process. And of course, even though if you get some lot of benefits, there are some cons also. Of course, we have to spend a lot of money for the machines. So highly expensive, at least one machines, especially for metallic printer, you need to spend $200,000 to $500,000, and also you need raw material. So for this material, for these machines, we need to produce specialized raw material. For example, powder, we have to make spherical forms. Then only we can ensure the fluidity. Otherwise, we cannot ensure it. Okay, so therefore, mostly gas atomization we have to use on it. Then only we can able to produce the spherical form, or at least we have to some sterilization technique people they will implement on it. So it consumes lot of expensive technique by which you can produce a spherical powder, because ordinary powder we cannot able to print on it. So filament manufacturing, wire manufacturing. So these are some expensive. That's what they're telling, expensive technique. Limited material. So as of now, we cannot apply for all the materials. So some polymers, some metallic materials, some ceramic powders, metallic powder can able to apply the AM technique. Some lack of access. So cost of lack of access means still people are having some patent. So there is a restriction to usage on the 3D printing machines. Slow for mass production. Yes, mass production may not be suitable. Okay. So these are some drawbacks for this one. Like now, let's focus on VAM technique, viral additive manufacturing. So it's also very, initially I told you, very simple technique, cost effective technique. So all kind of thin wall cross section, especially large wall, large size of the product can be easily produced via the wire arc additive manufacturing. Yeah, just now we have seen the video also, right? So what is the concept? Very simple. So here the raw material will be in the form of metallic wire. It has to be sent to the robot controlled arm, okay, welding torch or something, or CNC gantry controlled system. So we have to send the filament. Okay, and before starting the building the product, so we have to use a substrate. So the substrate is also to be selected carefully. So whatever the material you want to build it, accordingly you have to select the substrate. Selection of substrate is very important. And before building, we have to clean it completely. So the both substrate, wire, the robotic arm, the torch tip, all should be properly cleaned. Okay, and we have to use shielding gas. We have to use either argon or helium. Shielding gas are to be used. Then only we can avoid the oxidation. Otherwise, a lot of oxygen will be embedded. Oxygen will be embedded or will be embedded in the structure of the the build product. That will affect the mechanical property completely. Okay, these are some precautions we have to clear, and moreover, we have to select the right voltage, correct feed rate. Okay, correct feeding of the wire. Okay, correct voltage, correct current. We have to apply it, and moreover, plus we have to apply correct quantity of the shielding gases. All these are 4 important parameters. So then once you optimized, then we can start the printing the parts. Okay, right. So here, for example, in the wire additive manufacturing, so the filler, okay, so it has to be connected to the wire. It has connected to the power supply, and workpiece also will be connected to the power supply. Once give the power supply, the feed will try to feed the wire. The moment it's come to them near to the substrate, near to the beginning, near to the substrate, arc will be generated. Because of the arc, the tip of the filler material will start to melt, and then it will be droplet out. It will be deposited. Okay, so then there is a continuous synchronization system. It will keep on feeding the rod and keep on producing the droplet of weld melt, and there will be a linear movement also by which we can able to build the layer. We can build the thin wall cross section layer by layer. Okay, so once one layer is completed, we have to wait for some time to extract some heat. Okay, for which we can do natural cooling, or we can pass some active gases also we can able to pass on it. They will call interpass cooling. Okay, then only we have to start the building. Otherwise, there are some defect like deformations, some deformations, some delaminations. Okay, and then some crack, warping. There are many issues also will come. So we have to do carefully. Right, that's what the VAM. It is a deposition date, cost-effective technique, and scalability. And mostly, I think we have discussed it. So the point is, as per the researcher, they are telling that even up to 10 kg per hour deposition rate is also possible in the VAM technique. Okay, right. Fine. So you can see this mapping of VAM process. You can see through the VAM. This is the mapping of the VAM. Okay, what are the properties we can obtain from the VAM component? So, for example, when through the VAM technique, we can get high building rate. We can have maximum volume size of the component. We can able to print it. Platform will be somewhat moderate flexible, and we can achieve high mechanical properties. And we can have full utilization of the materials, the filament. And then overall cost is also almost we can able to save it. Of course, there are some drawback. Surface finishing is a drawback in the VAM technique. Accuracy not as much high, high compared to the laser, powder fusion bed system actually. So the point is, for example, in the case of laser powder bed fusion technique, yes, any complicated product can be easily produced via LPF technique. More accuracy can be obtained on it. Surface finishing also will be good. Okay, but you can see the material utilization will be low. Then mechanical property somewhat low compared to the VAM product, and then maximum volume size of the product will be almost restricted. So there are more drawback can occur in the LPF, but only few advantages in the LPF only. The point anyway depends upon the application. We have to select it. So what we observe is the VAM technique can able to give lot of benefits. So that is the motto of this picture. Sorry. Right. Yes. So already I explained you. So how the VAM equipment. So VAM equipment consisting of, there should be robotic arms or CNC GAN systems should be there. So there is a robotic arm. The top there will be a tipped torch, welding torch will be there. So inside we can able to send the filler. Okay, or separately, or we can able to send along together also. And there are IR sensor, camera, and suppose in order to have proper feedback system, we can send we can mount some sensor, and all the feeding system, supply of the shielding gas system, all should be completely synchronized using the computer control systems. Right. Next, VAM design aspect. So what are the design aspect we have to focus on it? Right. So whenever we want to build the thin wall cross sections, okay, there are several design parameters we have to account on it as engineers. Suppose if the build thickness is too thin, then the wall will be collapsed. Okay. Suppose too thick, then material will be wasted. So we have to optimize the thickness of the bead. Okay, thickness of the bead. And apart from the thickness of the bead, the thickness of the bead are wall thicknesses. Apart from the wall thickness, layer height. Now we are talking the layer 1 by 1. The layer height, bead width. If more bead width, then there will be deformations, both along longitudinal direction. That is the the deposition direction or build directions. Okay, there will be some deformations or deflections will be happening on it. So bead width also properly optimized. Then overlap ratio, mostly 20 to 30% overlap should be there. Then only proper bonding will be carried out. So overlap ratio. So these are the important parameters we have to account on it. Okay. So and not only for that one, during printing, that means during VAM technique. So a lot of heat will be generated. Okay. So whenever you want to build the next layer, we have to wait some time to remove some heat. Then we have to start the building. And apart from that one, before starting the VAM technique, so we have to preheat the substrate. Then only, and the the weld deposition will try to add properly on the substrate. Otherwise, there will be a crack. Okay, so these are the important point we have to consider in the VAM design aspect point of view. Right. Next, deposition path planning or path planning is also one of the important things. Usually, majority people they will do linear interpolations. For example, as per this picture, we have to do linear interpolation. We have to give linear interpolations. For example, let us assume 100 mm length. Okay, you can give some 0 to 100 mm length. If you do the programming exactly on line, that means 2 command is enough. Okay, you can able to print quickly. Okay, but when you do layer by layer, there will be a the strength of the bond will be between the layer will be somewhat low only. So what the researcher found it mean, instead of doing straight path, so we need, if you give side to side or zigzag path, okay, so then the build part will have more mechanical strength. Many people proved it on it. Okay, that's what the point. So these are the design aspect we have to note it down. Right. Fine. Next one is, what are the steps to be followed in the VAM fabrication process? What are the steps to be followed in the VAM fabrication process? And there are a few steps you have to follow it: pre-processing, process parameter, selection of process parameter, deposition strategies, real-time process monitoring, then post-processing. So these are the 5 steps, or usually people they have to follow on it. Okay, right. Pre-processing mean what? Material selections. Okay, is an important one. As I told you initially, all material cannot be used for VAM technique. Selection of materials. Anyway, you can use steel, titanium alloy, aluminum alloy, and moreover, please understand that suppose if we would able to produce some simple shape using suppose we need some simple shape, we should not go for VAM technique. So we have to use conventional technique only. Then only we can save the cost. So whichever the parts cannot be produced by the conventional technique, and whichever the parts taking more and more time and more cost, then such a thin wall cross section you have to go for VAM fabrication processes. Okay, so that is one important point. Anyway, we can use especially for titanium alloy, nickel based alloy, steel product, VAM is the right choice. Even aluminum alloy is not good. So these are high strength material is highly recommended for the VAM technique, because in the conventional manufacturing technique, it is very difficult to produce some complicated product, but here it is possible. So then process parameter, already we discussed: current, voltage, travel speed, wire feed, okay, bead geometry, heat input. So all will depends upon all will define the mechanical properties. Okay, so there will then selection of shielding gases, at least argon or helium. Okay, gases to be used by which we can able to avoid the oxidations. Okay, also during the VAM fabrications, we have to ensure the arc stability. Then deposition strategies. Okay, so deposition strategy mean you can build single pass build. Okay, suppose whenever you want to build some large thin wall sections, 2-3 head, one head will go printing, then after frequent time, then second head will do the printing, then third head, that is what multi-pass depositions can be also possible in the case of VAM technique. But before that, we have to ensure the inter-pass cooling. Suppose we are not doing inter-pass cooling, then the second layer, suppose there is more heat, means when I build the second layer, so there will be more deformations, more deflections, and sometimes the weld structure will not be perfectly straight. Okay, so that is the drawback of that is the thing we have to keep in mind. Deposition strategies we have to follow we have to follow it. Then real-time monitoring. Whenever we want to have good build structures, so we have to try to use closed feedback systems. Okay, so as per the design, whatever not achieve as per designs, we need to use closed feedback control system. How can you achieve it? By placing cameras, thermal sensors, and all sensors, we can able to control the systems. We can able to produce the good product. Okay, that is what real-time process monitoring. Next one is post processing. Okay, yes, excuse me. All right. The last step is post processing. So post processing means, of course, once we have built the component, we need machining. Okay. Then only we can achieve the quality of the component. So we have to remove some layer, so that we can ensure the quality, or we can produce a high precise component. And for example, whenever you want to build from aluminum alloy, we cannot get good strength. So we have to follow some heat treatment. Okay. And important point is, as we are building the thin wall cross section over the substrate, okay, so there will be a storage of stresses. Okay, there will be a storage of stresses. We have to remove it. They will call residual stresses. Okay, they will call residual stresses. Suppose, for example, if you are not properly clamp the substrate, or suppose we are not giving proper clamping forces, then there will be a lot of residual stresses will be built in the systems. So in this case, what will happen once we unclamp it? So the residual stresses will try to make the crack, crack. So that is also we have to account it. How can you eliminate the reliable stresses? We have to properly do the clamping, and then we have to do some stress recovery processes. Okay, so these are the things. Anyway, in order to refine the microstructure, to improve the surface finishing, and in order to improve the fatigue life, we need to do some post-processing technique. Okay, so these are the VAM fabrication steps are to be followed. Right. Fine. So when we in the VAM technique, whenever we are doing the building the layer by layer, very well. So there will be a directional solidification will be carried out. Okay, there will be directional solidification process will be carried out. Accordingly, the bead will be cooled. Okay, right. So here, as I told before, interpass cooling. Once we done the first pass, still there is certain period of time heat will be there. Okay, before starting the second pass, we have to remove the heat. How can you remove it? We can pass some air, or we can pass some water. Okay, cooling system, we can arrange cooling by means of water, or by means of air, or by means of the gases. So by which we can able to cool the systems. Then we can do the second layer, then again cooling, then third layer. That's what they are calling interpass. Interpass can be achieved by naturally or by means of the fan or gas or liquid cooling. Okay, so or predefined time also we can do it. This is what interpass cooling. Right. Next, characterization of warm product. So characterization of warm product. Okay. So once we have done the build the component through wire additive manufacturing, there are many techniques available. So by which we can able to do the characterizations. So as engineer, we know very well. So once the product has been built, so we have to ensure the qualities. So then only we can expect the good performance from the particular product. So what are the concepts? What are the things are available? There is a scanning microscope by which we can do the elemental segregation. Is there any elemental segregations? Is there the structure is whether it is homogeneous or not? Okay, and then is there any porosity? Any crack is appearing on it? So for which we can use optical microscopes. What are the phases are formed? So for which we can use X-ray diffractions. Then X-ray photon spectroscopy. So what are the exact crystal structure formed in the VAM product? So we can use X-ray photon spectroscopy. Even in order to determine the residual stresses, where people are using the synchrotron XRD, high temperature XRD. Okay, so these are the common characterization technique. So by which we can able to characterize the one product. Okay, that's what the things. Right. One more point in the wire additive manufacturing, as the we are building the layer by layer. So most of the component will have columnar grinds and dendritic grinds. Okay, because of the build deposition, most of the microstructure usually will have a columnar grind and dendritic grind will be formed. Okay, this is the common microstructure will appear in the VAM product. You can see the pictures, SCM pictures. This is layer 1. There is a layer. The red line indicates the interface between the two layers. Okay, interface between two layers. And you can see there is a columnar grind structure is getting formed. Okay, and still if you have the magnifications, you can see there are some metal carbides, some elements are segregated. Okay, some elements are segregated which are presented in the inside the grind, which is inside the grind. They will call interdendritic grinds. So these are the microstructure usually formed in the case of VAM processes. Okay, that's what the point. That's it. And even some XPS technique, we can able to identify the presence of oxygens. Okay, mostly whenever we want to do the VAM on the titanium, so we have to use proper shielding gases and shielding quantity. Otherwise, there is a pickup of oxygen. Okay, so these are the things. Right. Next, there is another one. Very well. I think maybe some of you, some of those who have done PhD, I think have know about the ACM along with the EBSD, electron backscatter diffraction technique. So by which also one of the good technique by which you can able to clearly observe the formation of the grain size and everything. And you know very well, so internal microstructure is very important. Okay, if we have a very good homogeneous microstructure, good structure, we can able to good performance. Suppose the internal microstructure is consisting of some lot of porosity, okay, some some crack or something, mean the particular component will not give you better performances. That's why we have to do proper characterizations. Okay, so anyway, here one researcher he used ordinary viral additive manufacturing, as well as he introduced some ultrasonic impact. Okay, they used some another nozzles. So once they have done the VAM depositions, immediately he applied that research applied some ultrasonic impact to refine the grain sizes. You can see same materials. Okay, same materials. This is for along the transit direction. That means deposition directions. Okay, and this is what build directions. So you can see different microstructure. This is the transverse directions. This is the build direction. Build direction means vertically up. Okay, transverse direction means along the movement of the the torch. Okay, that's what the transverse directions. You can see the grain sizes are completely different. That's why most of the VAM product will exhibit anisotropic properties. Okay, so everyone people will say VAM product is only getting anisotropic property. How can ensure it? Okay, so through microstructural characterization we can able to ensure it. And further you can see this picture. Suppose when they introduced ultrasonic impact, after ultrasonic impact, immediately, I think a few seconds after the ultrasonic impact, so the grains are completely refined for same materials. This is what transverse directions. This is the build directions. So whenever we have the fine grain structure, obviously we can have the very good strength, mechanical strength. You can see this is the inverse IPF inverse pole figure images, and this is the corresponding grain size distributions. You can see here how the grains are shifted towards the low angle. More grains are more frequency shifted in lower angle. Therefore, this sample will give you more strength compared to this ones, because it has coarse grain structures. This is the way we have to do the characterizations once we build the component through VAM technique. Okay, right. And yes, this is what mechanical characterizations. So simply, I hope you can know that once we build the component through VAM technique, as I told you now, so most of the VAM product will exhibit anisotropic properties. It is not good actually. Some application is good. As much as possible, we have to minimize the anisotropic effect. Okay, so in order to check the strength of the build product, what we have to do? We have to cut the sample along the build directions, then along the transverse direction, and then we have to conduct the tensile test. Then we can able to see the behavior. Okay, for example, some researchers. Okay, so they did this is what tensile stress strain curve for along the transverse direction, build deposition directions. This is the tensile stress strain curve along the build directions. So build direction always getting weak. Why? There is interlayer. Okay, we cannot suppose if we ensure very good bonding. Okay, overlapping is also exactly correct. Then maybe the possible we can have both. That means we can achieve close to the transverse directions. But practically it's not difficult. Okay, so that's what the researcher they found it. Okay, and this is what after ultrasonic impact, you can see how much the strength is improved. How much after the same materials, but they introduced ultrasonic impact followed by the deposition. Okay, so that the property will be somewhat. We can, for example, you can see this. You can compare this tone here almost 190 or 180 or something megapascals, but here the same the build directions. I think 220 something, so 220. So this much amount of strength can be improved. So that's what the slides actually. This is ultimate strength value, yield strength value, elongations, even ultrasonic impact. Introduction of ultrasonic impact followed by the VAM depositions will produce will retain the ductility. That is the plus point of this VAM followed by ultrasonic impact. Okay, right. Fine. Right. Then I already told you. So X-ray diffractions. Through X-ray diffractions, we can able to identify what are the phases formed in the warm product. Okay, what are the what are the phases will be formed in the warm product? We can able to do the X-ray diffractions. You can see the we can easily find out the what are the phases formed in the X-ray diffractions. Actually, here you can see there is a ordinary worm. Actually, they have magnified the single to theta value, and then they found some magnification. There is a shift changes. So the shift changes indicate that there is a grain refinement in the case of ultrasonic impact samples. So my point is EBSD, okay, and then XRD, so on CT scanning. So these are the technique by which we can able to properly do the characterizations of the VAM product. Okay, so that's what the concept of this one. Through CT scanning, we can able to measure the porosities, and porosity is also not good. Okay, as much as possible, you have to minimize the porosity. Then only the fatigue life or creep of the VAM product will be very high. Fine. Then mechanical performance. So I think most of the concept, most of the things we have already discussed. As I told you, anisotropy VAM. So that means the property will be different with respect to the directions. That is some drawback. Okay, anisotropy VAM lead to layer-wise VAM will offer anisotropic mechanical properties. So as I told you before, vertical, whenever the build directions, the vertical build can show weaker interlayer bonding compared to the horizontal direction along the deposition directions or transverse directions. Strength and ductility. It is very difficult to achieve the strength and ductility in the VAM product. So in order to achieve the good strength and good ductility, so as we discussed before, you can introduce some extra technique like ultrasonic, okay, or some rolling, okay, some short peening. There are many techniques available, so by which we can able to improve the strength, minimize the anisotropy effect, and we can able to improve the ductility also. Okay, that is the strength and ductility. And then thin wall performance. Thin wall structure mainly depends upon the homogeneous structures. Okay, non-presence of the porosities. Okay, so that good and refined grain structure. Only the corresponding thin wall cross section can give us a good static load capacity. It can withstand fatigue load also, and high temperature creep also. It can able to perform on it. Okay, otherwise, if there is a residual stresses, will cause warping, some crack. So these are the mechanical performances of the warm product. Right? Yes, there is a challenges and the research on VAM. I think I hope you can able to follow me, right? If you have anything, maybe we'll discuss later. Huh? So
yes,
right.
sir. Yes, sir.
Yeah. Okay. Good. Right. Yeah, there are some challenges and research in the VAM. Okay. So current challenges means, as we discussed initially, poor surface finishing is the drawback of the VAM technique. Okay, and that means geometric accuracy will be low. Okay, so and there will be some spatter, some porosity, some hot crack, warping. These are the main challenges will involve in the VAM technique. Okay, there are some solutions to avoid this one. As we discussed before, you can introduce ultrasonic impact. Okay, followed by the depositions. Okay, so we can minimize this things. Or we can use hybrid VAM, twin VAM systems. Okay, or we can develop some machine learning algorithm by which we can able to we can use the optimum parameters. So by then we can place some intuitive sensors so that we can increase the efficiency of the closed loop control system, and by which we can able to get the better solutions. So that's what some challenges and research in the VAM product. Right. So now VAM also there are many categories. I think 4 or 5 we will discuss it here through this one. Anyway, it's not a new technology. Before we used gas tungsten arc welding, we have used MIG welding, from plasma arc welding. From this only electron beam welding. From this only people developed the concept. Okay, right. So gas metal arc welding based VAM, gas tungsten arc welding based VAM, plasma arc welding based VAMs. So this is what gas metal arc welding based system already discussed. Okay. Right. So, for example, principle of operation of gas metal arc welding. Gas metal arc welding operations. Here, the filler, the wire has to be passed on the welding torch, it has to be connected to the power supply. That means here continuous consumable electrode, wire electrode has to be fed through the welding torch nozzles. Okay, and then workpiece will be placed. That means there is a substrate. It is also to be connected to the power supply, and there is a shielding as a system also should be connected to the systems. So based on the programming, based on our design, based on our drawing, okay, so what will happen? The wire will be fed down towards the so near the initially there is no workpiece, near to the surfaces. The moment it's coming here, the spark will be arc will be generated. Okay, then once arc is generated, melt will be happen. It will be deposited on the particular area, and immediately there is a synchronous motion actually. It will move next point. Okay, so that's what. So electric current stuck between the wire tip and metallic substrate. Okay, so that's what the gas metal arc welding based MAM technique. Okay, so here deposition process. That's what first initially wire feeding, then arc formation will be carried out. So arc formations, you have to use proper stable electric arc between the wire tip and substrate. Proper voltage and current has to be given to the machines, and then we have to also properly send the shielding gases. Okay, if you send more, also not good. Less also there will be a possibility of deformations. Okay, more heat will be there. Okay, so and more oxygen pickup also, oxygen nitrogen pickup will be there. Then arc formation, then layer by layer build up, then finally cooling between the pores, which is called interpose cooling. These are the steps will involve in the gas metal arc welding based wire arc additive manufacturing techniques. Okay, right. Fine. In the gas metal arc welding based WAM technique, the metal transfer mode is important, like a welding. Okay, basically there are 4 metal transfer mode. One is globular mode. That means what? The filler will come, the wire will come. Okay, will make the arc. Then there is a spear forms. Melt will be formed. It will be droplet out by means of the gravity. Okay, usually the droplet will be the diameter of the spear, and the diameter of the melt will be highly larger than the filler wire. Okay, that is the filler wire. So that is what globular metal transfer. Globular metal transfer, unstable spatter. Yeah, anyway, globular one. Usually this will occur at low current, low voltage. Low current, low voltage time, it will kind of melt transfer will occur. Second one is short circuit. Here also low current, low voltage will appear on it. Okay, but the wire, when the moment wire touch on the substrate, touch on the part, metal part, then only arc will be generated. Okay, that is what the short circuit. Okay, this is the the globular that spherical shape droplet will be forming here. That is what globular metal transfer mode. Okay, and yeah, there are some drawback. So large molten droplet form at the tip of the wire. Mostly this kind of things will produce a lot of spatter, less stable arc, and big melt pool will be happening on this metal transfer. Okay, right. Whereas in the case of short circuit when it will happen, the moment the filler is touch on the substrate, touch on the previously built work pieces, then only arc will be generated. Then immediately that's what they're calling short circuit. Okay, so here also low voltage and current will be passed on the systems. When compared to the before one, maybe here somewhat we can minimize the spatter actually. I remember. So low heat input, less distortions will be there. Okay, so it is good for thin sections. It is good for thin sections. Then spray transfer. Both spray transfer and the mode and the pulse spray transfer mode. This is recommended for the WAM technique. Here high voltage current. Okay, high voltage current usually apply onto the systems. Okay, right. So spray means because of the supply of the high current and high voltage, the moment filler is coming, there is a gap. Immediately the arc will be formed and melt will be melt will be formed. Melt will be formed. Here what they are telling is the diameter of the melt spool will be very small compared to the filler one. Okay, so that means droplet size smaller than the electrode diameter. So here, because of the high current level and high current voltage, deposit it will be very high. Okay, minimum 100 to 200 cycles per second we can achieve on it. So that is the plus point of the spray transfer: high deposition rate, deep penetration, stable arc, or possible in the case of spray transfer. Okay, whenever you want to have thick sections, and warm thin wall, we can go for this spray transfer, but it also produces a lot of heat affected zones. So there are some drawback. Then pulsed spray. So here the current will be high current, but sometimes high current, then low current, high current, low current, high current, low current. So accordingly, the arc will be generated, and then the melt part will be forced towards downward directions. Okay, that's what they're calling pulsed spray transfer. Okay, used pulsed current waveforms. That means whenever high current is there, melt pool will be formed. Whenever low current is there, it will be forced, downward directions. That's what they're calling pulsed spray transfer technique. Anyway, pulsed spray transfer as well as the spray transfer technique can be recommended for the WAM applications. Okay, right. Fine. Anyway, when compared to spray transfer or even pulsed transfer, the accuracy will be very somewhat not that much expected good quality. More spatters, more porosity will be formed. That's why people invented cold metal transfer. CMT, if the WAM torch attached to the CMT concept, it is good. We can improve the structure of the WAM product. Okay, that's what they will call cold metal transfer. Okay, so here what is happening mean? It's very simple. So whenever the filler is the wire is coming, okay, arc will be generated. Metal will be dropped. In the meantime, the wire will be moved up, pulled up. There will be a pull and push action. There will be a push and pull, push and pull and push. Everything fraction of a second only. That's what they are calling cold metal transfer. So that means during dropping, the temperature will be almost minimized. Therefore, the heat dissipations over the spreaded area will be somewhat minimized. Okay, that's what they're calling cold metal transfer technology. Okay, I hope you can understand. There will be push and pull motion of the wire will be there. Accordingly, the system will be synchronized. It is invented by the Fronius in the scientist inventor name actually. Okay, right. That's what they have given cold metal transfer. So I also observed many articles. So whoever applied CMT technology in the WAM building a product, they got good quality, good mechanical properties. That's what the next slides. So here the CMT based WAM technique, wire approach the weld pool, create the short circuits. The current is reduced rapidly. The moment the arc is generated, then it will go to the current will be less. Then prevent overheating. Then wire retract slightly up, so the melt part will be detached from the wire. It will be dropped. Okay, that is the working of the cold metal transfer in WAM. Okay, so they have mentioned that cycle repeat 100 plus times per second. 100 droplet per second it will be formed. Okay, right. Yes, when compared to other metal transfer technology, CMT is the best one. Low heat input. Okay, so because how the low heat input, because it reduces the molten pool. Okay, so therefore obviously the heat input spreading will be minimized. That is the plus point of low heat input. Improved surface finishing, enhanced material properties. Of course, if we have a good microstructure, we can have the improved material properties, and better for thin wall fabrication. Even 1 to 2 millimeter, very thin wall also can be fabricated via the cold metal transfer technology. Okay, and also we can get more energy efficiency from the particular product. There are some challenges also. Complex equipment, so we need to do synchronize the pull and push, pull and pull, pull and push, pull and push the the wire. So the equipment synchronization is somewhat difficult when compared to the other WAM equipment. It requires advanced digital power source and wire control. Deposition rate somewhat slower when compared to the other technique, and the process is highly sensitive. Okay, so that's what the things. Application very vast: aerospace, automotive, energy. Even for research work, people are using the CMT based WAM technique. Okay, right. Next, gas tungsten arc welding based WAM technique. It's similar to before, but here, as you know very well, tungsten electrode will be to be used as a electrode here. Wire will not be act as a electrode actually here. Only will act as a feeder. That's what the difference between the previous one and this one. Here, because of the using of the tungsten arc, the arrow will be somewhat narrow compared to the previous one, and good surface quality can be achieved from the gas tungsten arc weld based WAM technique. So that's what the things. I hope you can understand the basic concept. So here only the challenge is the synchronization of, we have to maintain the constant gap between the tungsten electrode and then the substrate or the previously built part. Okay, synchronization, we have to maintain the constant gap, and then we have to always keeping the feeding of the, and then synchronization of the gases, synchronization of the travel. All these are highly challenges. Okay, so remaining and all thing, but what I observed is we can have good quality when compared to the gas metal or weld based VAM technique. Okay, so arc initiations, wire feeding, layer by layer deposition, build deformation, these are the usually building will be, these are the steps will be involved in the technique. Okay, right. Advantages of gas and arc weld based VAM: stable arc, high quality can be achieved, and very good surface finishing, quality product can be produced via this technique. Any material can be flexible because here filler will not act as the electrode. Okay, even that's why reactive metal also we can able to easily build it. Titanium, aluminum, nickel alloy is highly best, and small heat affected zone when compared to the previous VAM technique. Okay, of course there are some drawbacks. Deposition rate will be somewhat lower. For example, 6 to 10 kg per hour can be achieved in the gas metal arc weld based VAM technique, but here 1 to 3 kg and less suitable for very large build. Okay, so there are some processes also complexity because we need to synchronize all the wire, gases, and then welding torch. Okay, and equipment costs also will be high. Then plasma arc welding based VAM technique. So here constructive, arc will be there, and via we have to pass the plasma gas. Then whenever the plasma gas passes on the constructed arc, it will be ionized. It will be ionized, which is called plasma gases. And there are 4 phases: solid phase, liquid, gas phase, and then plasma phase, the plasma state. Okay, at the high state, the plasma state, temperature will be very high. Okay, only thing, so the plasma arc welded basing VAM technique, we can maintain constructive, very narrow arc can be generated when compared to the tungsten TIG welding, TIG based, VAM technique or gas metal arc welding based technique. Here we can maintain a constructive narrow arc by which we can minimize the heat affected zones. We can build the good quality of the build on the VAM product. That is the plus point of the plasma arc welding based VAM technique. Okay, so anyway, it's related to plasma arc welding only. Okay, so that's what the things. So arc generations, wire feeding, layer deposition, controlled heat, these are the steps involved in the plasma arc based VAM technique. Here high energy density, the energy, that's what, once the plasma is generated, the temperature will be around 10,000 to 20,000 degrees centigrade. So the energy density will be very high, almost 3 times higher than the gas tungsten arc weld based one. High energy density can be achieved, and moreover we can get narrow arc, narrow droplet of the things. That is good for the product. So better control precisions, good surface finishing, lower distortion, heat affected zone when compared to the previous technique. Okay, this is what plasma arc welding based thing. Of course, there are some drawback: lower deposition rate, equipment cost will be more, and process will be somewhat complicated. Applications are very wide. Then multi-wired VAM machines also available. Multi-wired system is also available. Single wire feeding, there are some drawback we have observed in the VAM technique. So for which we can use twin system. Okay, that means we can feed 2 wire in a single nozzle, or you can use 2 nozzles. We can have two nozzle can be mounted in the robotic arms, and we are separate to robotic arm, and we can able to synchronize on it. Okay, so that's what the multi-wire arc based VAM technique. So by which we can improve the deposition rate. So building will be very fast, and whatever the alloy, suppose any new alloy we want to develop it, thin wall cross section, or we want to build a metal matrix composite based thin wall, we can able to build on it. That is the plus point of the multi-wire arc based VAM technique. Or we want to build a functionally gradient layer, some layer, for example aluminum, some layer copper, some layer aluminum, some layer titanium. So we that is what they will call functionally graded layer. So for which the multi-wire arc based technique can be used. Okay, so that is one technique. There are many categories. Tandem wire based technique. 2 wire can be fed into the same molten port. That is what tandem wire VAM technique. two wire will be passes on the single nozzles. Okay, that's what systems. So here deposit will be, you can see 15 to 20 kilogram per hour. For single wire, 10 kilogram. Just we can, the deposit rate will be high, almost double. That is a plus point of the tandem wire WAM technique. Or cold and hot wire. One wire maybe passes on the nozzles, will act as electrode. Other wire we can, we can introduce as this secondary one. We can call cold wire. This is also another technique. You can understand. Cold wire and hot wire. Hot wire usually passes on the nozzle. It will be connected to the power supply. Will act as electrode. Other wire will act as a cold. Anyway, by which we can improve the deposition, or what we want to improve, we can customize the alloy systems. Okay, that's what the cold and hot wire feeding systems. Dissimilar, different alloy also, different wire can be fed together, or twin torch, two welding torch can be also used. These are different types of multi-wire or based WAM technique. You can see the sketches. I think wire feeding, arc generation, droplet, solidification, these are steps will involve in the same like before. Okay, right. So high deposition, alloy will be flexibility, tailor mode composition can be achieved. Whatever the composition we want to build on the product, we can able to build on it. Okay, and multi-material graded structure can be possible, and the process efficiency will be very high. So these are the anyway, according to the application, we have to go for right one technique. Of course, there are complexity. Okay, so complex or control. We have to there will be a lot of challenges. Multi-arc, controlling of the multi-arc, wires can interfere, arc flow instabilities, more complex equipment, heat management systems, cost. There are some drawback. But as I told you before, any kind of material can be tailored. That's the plus point of this technique. You can see. So please understand that any product, any thin wall cross section can be easily made through the WAM technique. Okay, because the way we are using multi-axis robot arm, so by which it's flexible. It's flexible. So whatever the orientation based on the drawing, it can tilt, it can build the product. Okay, and also you have seen the video also. Right. Next, we'll focus on few minutes development of metal parts via WAM process. So each and every depends upon the material. There are some some researchers they face some issues. I read some articles, and according to their points, I have highlighted some points. So some people, they have built a titanium alloy, and I initially told you for titanium alloy, steel-based alloy, okay, then nickel-based alloy, high-strength material. It is whenever we want to build parts for high-strength material, WAM is the right choice. For lightweight, simple component, it is it is useless one actually. We have to use conventional technique only. Right, titanium alloy. So mostly, most of the aerospace component made from the titanium alloy. Okay, right. So WAM, it's attractive for large and complex titanium component. So in the most of the people, what they observed is, they have observed different microstructure, inhomogeneous microstructure. When after building, they found inhomogeneous microstructure. That's what. Okay, by inhomogeneous means bottom, the same build with bottom, sorry, friend, you can see, imagine top view, okay, or in the front side, bottom side one microstructure, middle region one microstructure, and then top region microstructure. Different microstructure they have observed. So according to the property will be completely changed. For example, this is the titanium 6 aluminum 4 vanadium alloy after the 3D print, after WAM technique. This is the I think bottom region. They have observed a lamellar structure. You can see line by line, lamellar structure, alpha matrix structure they have observed. Then some area fine basket waveform structure. Then I think this is middle region. Middle region again nominal matrix structure they have observed. And again fine basket wave, and then matrix structure formed. So it depends upon distances. The structure is completely not uniform. Okay, that is some challenges in the that is the microstructure they observed in the titanium 6 aluminum 4 vanadium alloy systems. Okay, right. Okay, that's what the things. This already explained you. Right. Next, yeah, of course, mechanic properties. So people, I will show you some tables also. As I told you initially, the build direction has low strength, high elongations. Okay, whereas the strength along the transfer direction, they got very high value. Deposit direction, they got high strength, lower elongations. So this alloy is also exhibited anisotropic properties. because of the presence of the different microstructure in the samples. Okay, right. You can see several people, developed a VAM product from the titanium 674 alloy. So they observed, most of the people, they observed columnar structure or lamellar structures. Okay, and they have tried to compare to the cast counterpart. Almost some people they have achieved, even some people they have more than the cast counterpart. Okay, but only the drawback is what they observed is anisotropic behavior. Okay, yield strength, ultimate strength, elongations. Right. Then aluminum alloys and steels. Okay, aluminum alloys also can be recommended in the VAM technique for 2 series, 4 series, 5 series. If you need any large, complicated, thin walls cross section, then only you have to go for a VAM technique. Otherwise, no need. There is no need to go there. Okay. So otherwise, conventional technique is always suggested one. Okay, right. If still people are facing 6 series, 7, I think last year I filled 6 series I used. Actually, I have done 2-3 work. Still, we are doing some analysis, and our work is not yet published actually. But 7 series, because of presence of silicon, more in silicon, there are some challenges to build the parts. Mechanical properties. So people developed several aluminum alloy. I will show you some tables. Okay, they observed that as built condition, most of the VAM product exhibited inferior property compared to the cast or wrought alloys. But after heat treatment only, okay, they have observed a good strength, significant improvement. They have observed on it. You can see there is one author. They have they have taken aluminum copper alloy, wrought alloy. They have mentioned the strength as fabricated. You see 128, 267. But after heat treatment, 305, even more than the conventional systems. That's why heat treatment can also improve the VAM product. Okay, even the ductilities or elongation, you can see 14%. But here, maybe for more than 4. Okay, somewhat good ductilities. Right. Next, nickel-based superalloys. Nickel-based superalloys also very important, and you know very well. Most of the aircraft component, space component, the engine mostly made from the nickel-based superalloys. So for which VAM is a very good right processes actually. Okay, so because high strength also we can obtain on it, and yeah, so even the strength of the material will be retained more than 550 degrees centigrade. So mostly Incon 718, 625 alloy are the commonly recommended material for the aircraft application, and in which people applied a VAM technique. Okay. So in the nickel-based alloy, mostly people observed large columnar grain, and they observed some lay phase, some precipitate metal carbides also they observed. These are the structure they formed: columnar grain structure and interdendritic boundary with lay phases. Some second phases, some metal carbides also formed. For example, in Cone 625, they observed a columnar dendritic structure with the lay phase, metal carbides, and some nickel niobium intermetallic phases also observed. So in order to improve the product, people they did some post-process heat treatment by which they have refined the dendritic arm size. We have to minimize the arms. The columnar grain is also not recommended one. If any material having columnar, mean what? Along the directions, it can produce a good strength. But if there is any load perpendicular to the columnar grain, the structure will not be withstand the materials. That's why some post-process treatment, some rolling, okay, some forging, okay, some heat treatment is required to refine the structures, grain structures. So by which we can improve the properties. Okay, and this is what some images they have. Some people observed from the nickel-based superalloy. You can see there is actually this is a columnar grain structure. This is a columnar. You can see the columnar grain structure. Then they have done magnified view one. Here they observed some layers phases, some delta phases, some metal carbides. Different phases was also observed. Okay. If these phases usually support for the strength, if these phase formation is very high, then it will degrade the mechanical properties. We have to do proper heat treatment, then only we can get the proper mechanical properties. And you can see in the VAM technique. So through VAM, in kernel 7.8, they achieved 473 megapascal ultimate strength. Also, they achieved very good mechanical property achieved from the VAM technique. So now my point is, through VAM also we can build the super nickel-based super alloy product with high strength. So there are many people. Okay. There are many people. They have fabricated the component from the super nickel-based super alloys, right? Of course, there are other metals also. People magnesium alloy. Even I purchased recently some magnesium alloys. We are doing some work actually, or even you want to build some intermetallic compound, iron, aluminum, iron, aluminum, or aluminum titanium alloy. So, or we want to build bimetal structure, steel nickel, steel bronze. So all these applications we can apply the VAM techniques and we can build the component. There are some people already applied the VAM technique for bimetal applications also. Okay. Then next one, yes. What are the common defects we'll observe in the VAM technique? Okay. Basically, porosity is the main thing, especially gas metal alkali based VAM technique. More and more porosity will be formed. Okay, because of the status. Okay. And suppose there is no, if you are not properly choosing the parameter, more porosity will be there, and high residual stresses also will be there. A high amount of residual stress will be there. And whenever there is a high residual stress, obviously there will be a crack. There will be a crack. So whenever the build component, VAM component, having some porosity, some value of residual stresses, some cracking, and definitely it will affect the fatigue life of the component. Okay, these are the some common issues. Sometime delamination. That means when we build the layer, it will not stick. It will be coming out. That's what they will call delamination. That is also possible. So we have to try to avoid it. These are the general issues we'll observe in the VAM technique. Okay. What are the causes? Poor programming strategy. Path planning is important. Weld pool, instability, wrong parameter selection. There is a possibilities. Thermal deformation from heat accumulations. There is a possibilities. Environmental factor, shielding gas contamination. The shielding is not pure, then there is a possibilities of a thing or malfunction. These are the root causes for which these are the defects usually found in the VAM product. And some articles, and I refer some review articles. Many people observed some time the titanium alloy severe oxidation, because titanium alloy is highly reactive. Okay, therefore, if you are not properly using the inert gases, then oxygen pickup will be very high. Then zinc, then titanium. For aluminum alloy, most people they observed porosity, because of the low melting element. And during ore formations, if the heat is very high, then porosity will be formed. For steel, they observed poor surface roughnesses. Okay, and for severe deformation, cracking. These are the common defect usually observed by the peoples. Okay, right. And this is already we observed. For example, you can see this is a mapping of the different materials actually. This is slides explaining. For example, titanium. Okay, this aluminum more in porosity, less some moderate deformations. Okay, surface finishing, high surface finishing. Sorry, this is surface finishing is low only. I think here some I think I just say a crack will be less in the case of aluminum. Crack you can map, so this is the mapping observed from different materials. So here usually, for example, bimetal, I think bimetal introduced a lot of residual stresses. Delaminations, where is nickel alloy introduced a lot of delaminations. Okay, where is minimum delaminations? Titanium, aluminum, steel produced less delaminations. Okay, so that's what the things. And these are the some properties. Maybe you can refer my slides. Already have my I sent all my presentation material to the coordinator. You can get from my slides. Right. So these are the people observed. Okay, right. Now I want to show you some deformation residual stresses. Okay, right. You can see, for example, if you do proper clamping, the stress distribution will be uniform. If you are not using proper unclamping, there will be a non-uniform stress will be accumulated. So this is what residual stresses. Wherever there is a residual stresses, obviously there will be distortions will be happening. Okay, that's it. To minimize the distortion, lot of technique will be there. We'll discuss it in another slides. So part distortion, geometric inaccuracy, layer delaminations, reduced fatigue performances, all these will affect the performance of the component. What are type of deformation will be there? Longitudinal shrinkage during weld deposition, along the deposit direction, shrinkage will be there. Transfer direction, there will be shrinkages. And then bending also will be there, bending distortions, angle distortions. These are the type of deformation usually observed in the VAM processes. Right. When the residual stresses will be accumulated. Suppose if the residual stresses is more than the ultimate strength, then crack will appear on it. Suppose the residual stresses is in between, above the yield strength, below the ultimate strength, then warping or plastic deformation will be carried out. So the amount of residual stresses will affect much. As per what is our ultimate aim, we have to eliminate the residual stresses. If the amount of residual stresses is more and more, then the crack or formation of warping depends upon the magnitude of the residual stresses. Type of defect will be formed. Okay, that's what the intent of the slides. Okay, and then material observations for some people observed for bimetal, they observed the highest residual stresses. That's what I have shown you before. Okay, intrinsic parameter. So we have to properly select the weld current, voltage, wire feeding speed, ambient temperature, proper shielding gas flow rate, and proper path planning, programming path planning. These are the things by which you can minimize the deformations. Then control strategies, intra-pass temperature control, proper path planning, post-pass treatment. These are the some mitigations. Then porosity. Porosity is also formed. You can see the porosity here. You can see there are a lot of porosity. Okay, so common in the VAM technique, especially for aluminum alloy. Whenever there is a more in porosity, maybe I will take 2 to 3 minutes extra, if you allow me. Okay, so we will try to finish within 5 minutes. So low mechanical strength, and whenever there is a porosity, it will affect the mechanical strength, and obviously fatigue life of the common affected. Okay, there are how the porosity formed, either raw material based. So I told you, aluminum alloy. If you are not using mostly, if you are not choosing giving the proper parameter, lot of porosity will be formed. Okay, or process itself, there is a possibility of porosity formations. So contaminations on white substrate will affect on the porosity, will make the porosity absorbed in molten pool. So whenever there is a contamination, it will absorb the molten pool. It will affect it will make the porosities. Okay, so because aluminum alloy highly susceptible at high temperatures. Okay, that's the important point. So non-spherical pores caused by poor path planning and unstable deposition will process. That's what process induced porosity. So what we can do, AC, gas metal alcoholic systems, or CMT based systems, high quality shielding gases, cleaning of wire, substrate surfaces, high quality feedstock materials, and then optimize the bead geometry. So these are the way by which we can able to control or mitigate the formation of porosity. Okay. Then the third one is cracking. Crack also formed. Okay, whenever there is especially whenever you want to build the bimetals or different materials, so there will be a thermal coefficient of thermal expansion will be different material to material. So we have to do preheating and we have to do proper parameter. Then only we can avoid the crack formations. Otherwise, there is a crack formation. Crack formation not only for that purposes, during solidification itself. Okay, so the grain formation, one grain formed immediately, other grain not formed, means there will be obstruction in the grains. Then crack will appear on it. Okay, or boundary morphology differences, grain boundary morphology differences, or if there is any formation of some inclusions, some precipitates. Okay, that will also form the crack. Okay, so these are the way crack will be formed. If there is insufficient remelting or coefficient of thermal mismatching, then there is a possibility of delaminations. Okay, these are the defect. Mostly will occur bimetal combinations, including alloy, nickel based super alloy. Last year I developed and we observed delamination. Then we found the solutions actually. Then how can we eliminate? You can see the crack. You can see the crack, and then there is a delaminations. This is the delaminations. Mixed to wire with optimized compositions. If you are not using proper cooling rate, then if you use proper cooling rate, we can able to minimize the crack formations. Preheating the substrate, we can minimize the crack and the delaminations. The last one is post-process treatment. Okay, post-process treatment. Yeah, in order to improve the strength of the mechanical properties of the VAM product, we can do either post-process heat treatment, okay, or we can do inter-pass cold rolling. Rolling we can do it, or we can do inter-pass cold rolling and inter-pass cooling, frequent cooling, or we can do short peening and ultrasonic impact treatment. These are the 4 methods so by which we can able to improve the properties of the VAM product. Okay, we will finish it now. That's what post-process heat treatment. Okay, so many authors, I read some articles. For example, after heat treatment, 4% of strength was improved. For aluminum alloy, 78% of strength was improved. For nickel-based alloy, 5% was improved. So you see the properties of improvement of after the post-heat treatment. Okay, so the purpose is, of course, we have to reduce the residual stresses. We have to improve the mechanical strength and the ductility and hardness, and we have to refine the grain stretch. Obviously, the strength of the VAM product will be improved a lot. Okay, after heat treatment, this is one method. Okay, and there are some key considerations no need for. Yeah, depends upon the material analysis. The heat treatment should be selected based on material analysis systems, pre-treatment state, temperatures and process conditions. Okay, for high carbon material, we need to do heat treatment. Right. Next, intra-pass cold rolling. You see, after building, after after making one layer, then there is a roller will come. Okay, we'll build we'll squeeze it. Okay, therefore we can avoid the porosity, we can avoid the stresses. That is what intra-pass cold rolling. Okay, so by which we can minimize the porosity. Obviously, once porosity is minimized, the strength will be improved. Okay, so already many people observed the improvement of ultimate strength, yield strength after cold rolling. Okay, every layer there is another system will do the rolling options. The last one is inter-pass cooling. Yes, inter-pass cooling already explain you beginning of the thing. You can see this some university have developed. So after building the layer, there is a cooling system. There is a cooling system will pass the coolant. Okay, then they will do the deposition, then cooling. So that's for inter-pass cooling system by which we can improve the properties of the VAM product. So we can have the less surface oxidation, refine the microstructure, improve hardness, enhance strength. These are the improvement you can obtain from the inter-pass cooling. And finally, short peening. I think as a mechanical engineer, very well. Short peening and the ultrasonic impact, we can able to improve the mechanical properties of the VAM product. Even for example, that's what. So for cold mechanical treatment applied to surfaces, it reduces the tensile residual stress and also improve the weld and path properties. Already there is residual stresses. If you pass the short peening, it will reduce the compressive stresses. That both will be balanced. Therefore, the stress will be relieved. Okay, that's why by means of short peening as well as ultrasonic impact, we can improve the strength. That means we can relieve the stress, we can refine the grain structure, and we can improve the performance of the VAM product. Okay, so that's what the some concept. Already some articles, some authors, they proved surface residual stress reduced by 15% after ultrasonic impact, and micro hardness increased by 28%. Okay, but there are some drawback faces only. It cannot go in both short peening and ultrasonic impact. It will not penetrate in entire thickness of the wall. Only some up to certain layers. For example, you can see up to 60 micrometer or 50 micrometer only there will be impact. Okay, that's what the things. So these are the references, and I hope somehow I will be able to deliver. Maybe you might have observed some new things from me. I will be very happy. Okay, so if you got some good point from my slides, and yeah, if you have any questions, and please welcomes, I'm ready to answer you. Thank you all very much.
Participants, if you have any questions, you can ask. Yeah.
Good evening, Professor.
Yeah, good evening, sir. How are you, sir?
Yeah, fine. Sir, from the first slide to 93rd slide, so what kind of efficiency level you are having? It's amazing. It was really, every slide was very impressed, very informative, very presentation.
Thank
amazing.
You, thank you very much. Yeah, thank you. Yeah, thank you. The only thing we have to, my aim is, I want whatever I learn it, I want to share my knowledge to our community. So we have to develop our skills so that we can, it will be good for our nations and good for the world. That is the main objective. Right.
Yes, sir. Yes, sir. We gained points from these your slides. I have only one doubt. Not
please,
doubt. I would like to get some clarification from your point of view. You told that powder, powder is in the spherical shape.
Yes.
Is there any scientific reason behind that spherical shape rather than remaining shapes and all, apart from that sticky phenomena?
Yeah. The reason is, suppose the powder particles are irregular, mean it cannot flow. So we need to have proper flow. We have to ensure the proper flow of the powders, flow of the materials. Okay, that's why spherical powder is very compulsory to be used in the DED technique, direct energy deposition technique, even for LPPF also. So otherwise, powder will not flow on it, and we cannot build the component directly. So that's why DED is that's why for DED, especially for DED, we have to have exact, almost spherical shape powder. Mostly it's possible. Only we have to use the gas atomizations. Even people tried through water atomization. Water atomization also powder shape almost somewhat irregular shape. Then people developed a gas atomization technique, and by which we can able to produce the spherical powder. Suppose if you have some developed new powder, new composite powder through ball milling or some other technique, what you can do is, you can do through plasma spheroidization technique. Through plasma spheroidization technique, you can convert irregular shape powder into spherical shape. Then only you can use as for the DED technique. Yeah.
Okay, sir. Thank you, sir. Thank you so much for your clarification. Thanks a lot. Thank you.
Yeah, good.
Any other questions, sir?
Sir, here,
Questions?
Dr. S. Raghunathan from Mohan Babu University, Tirupati.
Yeah, good, sir. Welcome, sir. Yes, please.
Sir, really wonderful lecture, sir.
Thank you.
It's a kind of eye-opening and for the beginners. Okay, but I have small doubt, sir. Actually, you explained about CMT technique as well as other TIG and MIG using in deposition of layer by layer. So see, in TIG, MIG plus CMT, each process has its unique characteristics in deposition of metal.
Yes.
So now coming to the development media, new alloy, right? So which particulars we have there? I have doubt, because CMT again very good process. We want spray mode or we want dip transfer, whatever transfer you want, you can use it in CMT.
Yes.
But when we can choose, how we can choose, it's a little bit confusion is there, sir. Whether we have to go for CMT or we have to go for TIG or MIG. How it is?
Yeah, suppose if you want to have deposit that is very high, mean no need to go for CMT. If you want to have more good quality product to minimize the porosity, to minimize the spatter, of course we should go for CMT technology only.
Okay. So only for deposition
quality of the quality of the product you want, accordingly you can go for CMT or without CMT.
Okay, but anyway, in irrespective of material, finally we need a quality material only, right?
Yeah,
irrespective of metals.
So in this case, CMT is the best. CMT is the best.
But then how this plasma we can, sir, actually individual process has its own nature. Then how we can compare?
Yeah.
So we could not compare, right?
Yeah, you're right. We will not compare, but plasma mean you can have the high quality product. Suppose let us take a titanium based alloy or any metals. You can go for gas metal arc welding. Also, you can go for gas metal arc welding without CMT, with the CMT, or you can go for plasma based. And definitely, plasma based system will give you good quality. So based on the facilities available and based on our application, we have to decide. We have to select the processes.
Okay. Sir, and one more thing, sir. Actually, suppose I'm having aluminum wire. For example, say 5000 series or 6000, any series. 6,000, for example, 6000 series. I want to make a composite material, like adding one more material in the wire form itself. So how in single layer we can mix these two wires, or first layer will be aluminum and next layer will be another material how we can do, sir? In casting means we can mix it, we can dilute, but here only layer by layer it will be.
Yeah. That's what, so you have to use multi-wire BAM technique. Okay. So you should have 4 or 5 feed systems should be there. The feeding system, but all 4 or 5 wire can be coupled to the single nozzles, and you can build it.
Okay.
For example, if you want to develop a high entropy PLI, it's also possible. People develop in China. Yeah, it's possible, sir. But you need a proper synchronization system. That's what I have shown in the picture. 4 or 5 feeder, whatever the alloy wire you want to. For example, let us take high entropy PLI. The famous one is Cantor alloy. Okay, iron, chromium, cobalt, iron, manganese, nickel. So all this wire compatible one. If we have 5 feeder, all 5 pure iron, pure cobalt, pure manganese, pure nickel. Okay, all 5 wire you can take all 5 feed for wire. You have to process on the single nozzles, and then it can able to produce, or you can build the alloys. It is possible, sir. Even composite also possible, sir.
So, but proportion, how can we control the proportion rate, sir?
You mean control? You mean control the synchronization of all the wire, or you mean?
So proportion means suppose in iron content it will be 90%, cobalt, moly, manganese will be 932 like that. So in feeding system, how we can call it? It will be very tough.
That's what synchronization. Yeah, that's what synchronization. For example, high entropy PLI, it's possible because all usually have equal atomic weight percentages, and accordingly, yeah, of course, that's what your point is correct. Feeding rate. Suppose, for example, iron density high. Okay, copper density is, suppose aluminum density is low. That means aluminum that wire should move very fast. Okay. In this case, I think yeah, there are some challenges. I get your point.
Yeah, that is missing, sir. Actually, I'm trying to calculate that only, the proportion, how to mix, how to control the proportion. There I'm held up. There I held up, sir. That's what. But anyway, really, sir, informative. I'm just a beginner for this VAM technique.
Okay, good.
Building background is there, but for VAM I'm new. So anyway, I got a lot of idea from your lecture. Thank you very much, sir.
Most welcome.
Yes, sir. Thank you.
Thank you, sir. Any other participants? Thank you, sir. Thank you very much. Nice was your presentation, sir.
So thank you very much, sir. Thank you very much.
You have made yes, sir. Your slides were very interesting to see, and it was grasping also, sir. Very much interested to see your slides at least. Informative session. I hope all the participants might have made use of this session, sir. Thank you very much.
Really, I'm very happy
for joining us.
I'm really very happy. Someone got many new points from me. I'm really happy, actually.
Yes, sir.
So, I best wishes for everyone.
Much, sir.
Yeah, thank you, sir. Thank you very much.
Thank you.
Thank you all. Thank you all. Thank you
very much, sir. Thank you all. So you can sign up, sir. You can sign up.
Okay. Shall I leave the session, sir?
Yes, sir. Thank you, sir. You can leave, sir.
Thank you.
Participants, you might have received the feedback form and feedback link of today's feedback link. You fill it tomorrow. And another 2 important sessions is that tomorrow we have 3 sessions, right? Tomorrow we have 3 sessions. The first session will be at 1:45 p.m. as we told already, and then it is from 1:45 p.m. to 2:45. And then the second session, there is no any change in the second session. It will be at 3:30 to 5 p.m. And the third session will be from 5 p.m. to 7:30 p.m. Okay. So tomorrow's 3 sessions will be handled by Dr. N. Jayant, Assistant Professor, Maulana Azhar, NIT. And then the second session will be on design and simulation in manufacturing by Dr. M. Malayappa, Director Pantech Solutions Private Limited. And the third session will be by Mr. Balamurugan, and then he's a solution expert, Petticoat Technology Engineering Services, Chennai. Okay. Please join us tomorrow by 1:40 p.m. Okay, please before 3 p.m. We'll start the session exactly tomorrow by 1:45 p.m. And fine. Another important thing is tomorrow evening after the third session, you will have the what to say questionnaire will be shared. In that we may ask the you have to fill it and send it to us within 1 hour. Right? Thank you very much. Tomorrow we'll meet at 1 p.m. Thank you all. Participants, if you are online, please enable your video so that we can take a screenshot of this session. Please enable your video, enable your camera so that we can take a screenshot of this. Thank you, sir. Thank you all. Thank you. Tomorrow we will meet by 1:45 p.m. Thank you all, please. Thank you.